Hello, hello. Hi. Welcome back to the stream. And today I'm going to read a book over here. I found this book. It looks interesting. So I want to read it. All right. It's called Homotopy type theory. Univalent foundations of mathematics. No idea what it means. But it's a book. Doo-doo-doo. Wait, how did I find it? Hot. Homotopy type theory. Where's the link? I guess this one can work. Oh wait. It. Neovide decrease of. No, I don't actually want to decrease the font size. Wait, this thing doesn't even work anymore? This is weird. I do have two neovides. Oh, because this is open. Um, Doesn't fit anyway. Alright, whatever. Set no number. Set no rel. No relative number. Alright, good enough. Alright. So what is this book about? This is about type theory because I'm making a programming language. I need to do a research of things. Univalent foundations of mathematics. Hi. Very nice Windows Linux. Kekloop, hello, hello. I'm using Hyperland. Okay, so we have a donut here with all of the mathematical symbols. Hyperland. Yeah, it's pronounced Hyperland, like this. It's a window manager for Linux or Wayland. The website doesn't open for me though. Of course, nothing ever opens. There you go. I need to improve my bar. This bar looks nice. Can I copy paste this thing that they are using? Book reading, my favorite? Yeah. Hello, Brainoid. Well, it's a specific book. It's a book about type theory, so, you know, it's not just any reading. Hello, how are you doing? I saw you released the demo. What's it called? Replicate. Wait, I don't have Replicate in my library? Did you not give me the Replicate? I thought I played it. Look at this, we have the demo now. Is demo different than the playtesting that was there? Or is it just upgraded to the demo now? No playtesting button anymore. Alright. The Univalent Foundations Program Institute for Advanced Study. So what does this word even mean? I have no idea. Univalent. Remaining unpaired during meiosis. Another term of monovalent. Let's not think about it too much, right? It's not different, it's actually even more limited, I see. So this is from 2013. Oh wait, book version first edition. Can I read like the second edition or something? Isn't there a second edition? Where's this website? Download the PDF. Are we reading the book with the replicate sounds in the background? Is there like a lot of music? I can download the demo. Sure. I usually don't run the music in the background, but I can. Oh, Steam was auto playing. Oh, oh wait, hold on. I'm not hearing it myself though. I guess because yeah, because that. Yeah, I was just not hearing it because it was on the headphones. The sound. Homotopy type theory is a new branch of mathematics that combines aspects of several different fields in surprising ways based on the recently discovered connection between homotopy theory and type theory. It touches the topics as seemingly distant as the homotopy groups of spheres, the algorithms for type checking, and the definition of weak infinity groupoids. Homotopy type theory offers a new univalent foundation of mathematics in which a central role is played by Voevodsky, univalence, axiom, and higher inductive types. The present book is intended as a first systematic exposition of the basics of the univalent foundation and a collection of examples in this new style of reasoning, but without requiring the reader to know or learn any formal logic or to use any computer-proof assistant. We believe that univalent foundation will eventually become a viable alternative to set theory as the implicit foundation for the formalized mathematics done in most mathematicians. What did I just read? Alright, where's the second edition? Hold on. There are not yet any plans for a second edition. Oh, really? Second edition. I just thought that, like, maybe since 10 years have passed, there is now a second edition. I guess not. Alright, whatever. Whatever. We did not set out to write a book. This present work has its origin in our collective attempts to develop a new style of informal type theory that can be read and understood by a human being. So someone who doesn't have a PhD? Is that what they mean? By a human being? As a complement to formal proof that can be checked by a machine. Univalent foundation is closely tied to the idea of foundation of mathematics that can be implemented in computer proof assistant. Although such formalization is not part of the book, much of the material presented here actually done present fully formalized setting inside a proof assistant and only later unformalized to arrive at the presentation you find before you, a remarkable inversion of the usual state of affairs in formalized mathematics. Right, let's maybe we will be skipping through things. I don't know. But here's the what the book is about, right? There is some type theory foundation. They talk about what is a function, what is a universe, what's a family, and then there's like dependent types, dependent functions, product, coproduct types, booleans, natural numbers, pattern matching, recursion, like this. And these words I understand. Propositions and types. This is something that I don't understand, I guess. But other than that, everything else I do understand. Homotopy type theory. Types are higher groupoids. Now this is where I don't understand much. Sigma types. Sigma type is just a dependent pair. Yeah. Sets and logics. Equivalences. Alright. Let's see. This is a new branch of mathematics. Yeah. Mastered 1738. Hello. Type theory was originally invented by Bertrand Russell as a device for blocking the paradoxes in the logical foundation of mathematics. Okay. Homotopy type theory interprets type theory from a homotopical perspective. Alright. So where's the useful stuff? Begins. Univalent foundation. Very briefly, the basic idea of the univalence axiom can be explained as follows. In the type theory, one can have a type whose elements are themselves types. Such a type is called a universe and is usually denoted by U. Alright, I understand that. Those types that are terms of U are commonly called small types. The like any type, U has the identity type IDU. Which expresses the identity relation A equals B between small types. Thinking of types as spaces, U is a space, the points of which are spaces. To understand its identity type, we must ask what is a path P from A to B between spaces in U. The univalence axiom says that such paths correspond to the homotopy equivalences A roughly equal to B, as explained above. A bit more precisely, given any small types A and B, in addition to the primitive type IDU AB of identifications of A with B, there is the defined type equiv AB of equivalences from A to B. Since the identity map on any object is an equivalence, there is a canonical map. Alright, let's skip through. Higher inductive types. One of the classical advantages of type theory is simple and effective techniques for working with inductively defined structures. The simplest non-trivial inductively defined structure is the natural number, which is inductively generated by 0 and the successor function. From this statement, one can algorithmically extract the principle of mathematical induction, which characterizes the natural numbers. More general inductive definitions encompass lists and well-founded trees of all sorts, each of which is characterized by corresponding induction principle. This includes most data structures used in certain programming languages, hence the usefulness of type theory in formal reasoning above the ladder. We finally managed to support polymorphic types in the type checker. It wasn't too hard. Yeah, I don't think it's too hard. Although, what did you... like, do you have, like... restrictions? Like trade bounds in Rust? Or do you only have the polymorphic type where, like what do you call those? No traits, yeah. Yeah, I guess if you don't have traits, it's like super simple. It's basically just a function which takes a type as an argument and returns a new type. Very simple. Although I don't like really have the inference, a very good inference for that yet, I guess. Like I only infer the concrete things. I don't know. There are a lot of improvements that I can have in my current system. So yeah, but the initial implementation was pretty simple, I guess. But I think traits are like complicating things, right? In the inference for sure. If conceived in a very large general sense, inductive definitions also include examples such as disjoint union A plus B, which may be regarded as inductively generated by the two injections. What's my barber's real job? What? What do you mean? What do you mean? May be regarded as inductively generated by the two injections. Hold on. I'm trying to read this sentence here. Inductive definitions also include examples such as disjoint union A plus B, which may be regarded as inductively generated by two injections A into A plus B and B into A plus B. The induction principle in this case is proved by case analysis. Alright, we are going to skip this. Oh, you don't see anything on the stream. Wait, what? I was reading the book. You don't see anything. I think it's OBS is weird. Well, you do see the camera. Yeah, you don't see it being updated. Why? Weird. Is this some Nix propaganda? Yeah, I'm reading this book here. The Homotopy type theory. The Univalent Foundations program. Whatever that means. Let me know if it like pauses again for some reason. What's this letter? A tombstone category? Hmm. The job of these people is to invent complexity and write books. It's rarely practical. Well, I know that this book talks about things such as the dependent types, which I wanted to like learn a little more about. I saw this book in referenced in multiple places, so if I could understand a little bit about it, maybe it would be a little bit useful, you know. but um, but like last time, I was reading about the subtype inference algorithm, and that paper was indeed, I would say, overcomplicated. The idea itself is like super simple. They might as well just describe it in one page, but there was like 100. I don't know if this book is like, I don't know. Let's just see what it's about. So here's the chapter 1, type theory. I don't think I need to read the type theory versus set theory. I don't know. Like, have you you tried reading things about polymorphic types as zero good resources? Yeah, all the things that I have read, they are like difficult to read, I think. But there are good ideas there. You just need to like really try hard to see the idea behind all the all the unnecessary complexity that is there. I don't know. Writing something that is easy to understand is difficult, I guess. So yeah. Writing is difficult for sure. Um all right, I will read through this. It's not that long, I guess. Homotopy theory is foundational language for mathematics. An alternative to Zermelo-Fraenkel set theory. However, because it behaves differently from set theory in several important ways, and that can take some getting used to. Explaining these differences carefully requires us. By the way, I was kind of reading one other thing. Like, you remember last time I was reading about subtyping, right? I don't know if your language is going to have subtyping. Do you plan subtyping or not? So so the reason I was like researching subtyping, because the effect system I thought should be done with subtyping. There is also, if we go for refinement types, for example, then subtyping also is being used there, I think. But I was like reading how Coca, the language, was doing it, right? So there's the paper that Coca developers did, Coca effects over here, another paper, right, from 2013. So you have like row polymorphic effect types. Since you have polymorphic types now, learning about row polymorphism, I think, is useful if you know what it is. I think this was Pretty easy to understand. It's not even that... Yeah, it's just like 10 pages. That's it. This one was nice. So one of the things, though, that Coca language did is in the early version of it, they were using subtyping. So in the earlier version of the Coca language, they were using subtyping for effects. And then later they discovered that using row polymorphism, it is like easier. I don't think they have any like good examples of how exactly it's easier, but like for example over here, right? This is the example. You have function foo, and function foo has two arguments of functions f and function g, which are being called inside, and then we also should do the error, right? So this means that the function, it can error, but it also can do anything that function f and function g can do, right? In terms of effects. So this means that this is the type of actual function foo, right? You have a one function that has like effects. What's this pronounced? I don't know, u1, and you have the other function with effects u2. So the effects of the actual functions is the union of u1, u2, and exception, the error, right? But this makes it very difficult to reason about, the union of the unknown variables. So then also I was thinking of doing it with subtyping. So that's what like Coca was doing, right? So with subtyping, you just say that the result is some new variable u3, which basically is so like the effects of function f is a subset of the effects of the function foo, basically, and the effects of function g is a subset of this, and then the error means that we have the exception effect is also a subset of the u3, right? So this is like the definition of the function now. You don't see what the benefit of the effects is in the low-level language? Well, you have like the allocation effect, for example, right? If you are writing a low-level language, you probably want to control where the allocation can happen, right? And like also I was planning to do the mutation with effects too, so for controlled mutation for safety. And what are the other examples? In a low-level language, I don't know, like in general, being able to access the whatever you call it, I mean, limiting access to the I/O, I guess, is useful in a low-level language too. I don't see why do you want like just a low-level language. Being low-level doesn't really prevent you from being high-level too. I think you can be both, which is the ideal, in my opinion. So anyway, this is what I was going to do basically for my language. This over here. So if I have a function foo which calls function f and g, passed to it as an argument, then this would be the type signature of this function, which is kind of difficult, right? Maybe it's too long. I don't know. But then with the row polymorphism, it looks like this. It's a little bit shorter. I don't know. This is the only examples that they were giving here. But anyway, you are looking into subtyping. I suggest you look into row polymorphism too, basically. Maybe it can solve your problem in an easier way. Because subtyping is like... So something allocates all the functions that use it that are colored with allocate effect. But then what? Well, you can also change the allocator, right? You like it's not only the allocate effect. It's also like you can have effect handlers. So like how exactly does the allocation happen? So in Zig, the allocator is being passed as an argument, as an explicit argument to all the things that need to allocate, basically, right? So through the effect system, it would be more of an implicit thing, but still checked, and you still can like change the allocator, which is useful, right? But for I don't know like how low level language you want to be. There are certain sections of code where you want to like ensure that no allocation happens, maybe because you want it to run faster, right? So you like make sure that the function is not like annotated with the allocate effect. All right, I didn't even start reading anything yet. Type theory is its own deductive system. All right. What's the useful stuff? Let me start with some useful stuff. Function types. All right, let's start with something that we already know, a function, right? Given types A and B, we can construct the type A into B of functions with domain A and codomain B. Like, why are they using these words, domain and codomain? Why don't you just call it an argument and the result type? We also sometimes refer to functions as maps. Unlike the set theory, functions are not defined as functional relations. Rather, they are a primitive concept in the type theory. We explain the function type by prescribing what we can do with functions, how to construct them, and what the equalities they induce. Given a function f from A to B and an element of the domain A, we can apply the function to obtain the element of the codomain B, denoted fa, and called the value of f at a. I mean, this is easy to understand, right? Given a function and an element of the domain, so this means like and a value of type A, we can apply the function to get the result. That's what it actually is saying. I don't know. My domain is exploding right now. Is this wizard knowledge? I don't think it's wizard knowledge, but they're using like wizard language for like some reason. I don't know. These people are mathematicians. Mathematicians are weird. You know? But how can we construct elements of A into B? There are two equivalent ways, either by direct definition or by using a lambda abstraction. Introducing a function by definition means that we introduce a function by giving it a name, let's say f, and saying that we define f, A into B, by giving an equation, this, where x is a variable and phi is an expression which may use x. In order for this to be valid, we have to check that f is of type B, assuming x is of type A. Now we can compute f a by replacing the variable x in phi with a. As an example, consider the function f from natural number into natural number, which is defined by fx is x plus x. We will define n and plus in the next paragraphs. Then f2 is judgmentally equal to 2 plus 2. If we don't want to introduce the name for the function, we can use the lambda abstraction. Given an expression phi of type B, which may use xa, as above, we write lambda x of a. dot phi to indicate the same function. So this is like they are just describing the language which we are going to use, right? So lambda argument, and then after the dot we have the body of the function, basically. All right. For the example in the previous paragraph, we have the typing judgment. Why do they call it judgment? I don't know. Who are they judging? Lambda x n x plus x is of type n into n. All right. As another example, for any types a and b and any element y, b, we have a constant function. This. All right. That's just an example of a function that doesn't use the argument. Sure. We generally omit the type of the variable x in the lambda abstraction and just write lambda x phi, since the typing xa is inferable from the judgment that the function lambda x phi has type a into b. By convention, the scope of the variable binding x is the entire rest of the expression unless delimited with parentheses. Thus, for instance, lambda x plus x would be parsed as lambda x x plus x. All right. Another equivalent notation is, all right, why do they have another equivalent notation? This arrow. Okay, so x into phi. Okay. All right. Why do they have like 3 different ways of like write? Like if you're writing a book, wouldn't it be easier for a reader to read the book if they only had like a single way to define a function? Why do they have like 10 different ways? I can understand like the difference between a lambda and like a named function, because this one is an unnamed and this one is named, sure. But like, why is there this third one? This is literally the same as a lambda. We may also sometimes use a blank in the expression phi in place of a variable to denote the implicit lambda abstraction. For instance, g x this is another way of write. Okay. By the way, what do you think about this? What do you think about this? I think something like Kotlin has it. So Kotlin, lambda it or something. So when you are writing a function, anonymous function, right? It. All words. Implicit name of a single parameter. It's very common for a lambda expression to only have one parameter. If the compiler can parse the signature without any parameters, the parameter does not need to be declared and it can be omitted. So like basically what they are saying here is this thing. So you have an anonymous function, right? So you don't specify that there is any arguments. So this over here in the brackets is actually an anonymous function which takes a single argument called it, and then it returns if it is more than 0, right? So the type of the function is it of type int, returning a boolean, right? But you just write it as it more than 0. So similar to that, you can just write in this book. So instead of it, they just use the hyphen, or like what is it called, right? So you just say gx and it, right, is basically a function that takes it and returns gx and y. This is kind of like nice sometimes. I don't think I have like really. I don't think I remember myself like wanting it too much, but I remember looking at Kotlin and thought it was nice, kind of. The only issue is like, where is the boundary of the function? So in Kotlin it's pretty obvious, because like the curly brackets are what are defining like a function. So it is the argument of this thing. But if in this book they are not having any, then it just like spends as much as it can. Like, for example, the other way to treat this would be to call a function g with argument x and a function which is the identity function, for example, because it's just returning it immediately. But I guess in this yeah, I don't know, we'll see. Now a lambda abstraction is a function, so we can apply to argument a. Then we can have the following computation rule, which is the definitional equality. So lambda x phi with argument a is phi. So phi quote is the expression phi in which all occurrences of x have been replaced by a. Continuing the example above, we have this is equal to 2 plus 2. Know that the function, we can construct a lambda abstraction, since this by definition, the function that applies f to its argument we consider to be definitionally equal to f. Hold on. What are they saying? Know that from any function f, from a to b, we can construct a lambda abstraction lambda x fx, which is same as f, right? Yeah. The equality, this equality is the uniqueness principle for the function types, because it shows that f is uniquely determined by its values. So did they specify what is uniqueness yet? I don't think they did. Type theory. They are referring to something that is defined later, I think, the uniqueness principle. The introduction of functions by definitions with explicit parameters can be reduced to simple definitions by using the lambda abstraction. For example, we can read the definition of f, which is this, as this. Yes, sure. Which is why they could just have only lambda expressions and not like all the 3 different ways to specify functions. When doing calculations involving variables, we have to be careful when replacing a variable with an expression that also involves variables, because we want to preserve the binding structure of expressions. By the binding structure, we mean the invisible link generated by binders. Sturdy pose. Hello, hello. Such as lambda, p, and sigma. The later we are going to meet soon, between the place where the variable is introduced and where it's used. Right, do I need to, like, I mean, I understand what a function is, right? I'm not sure what they are trying to teach me here. Now we have assumed somewhere that y is a natural number, then what is fy? Wait, what are they trying? When doing calculation, we have to be careful. If we assume somewhere that y is n, then what is fy? It would be wrong to just naively replace x by y everywhere in the expression. This, because this means that y gets captured. All right, they're talking about like the capturing and stuff. Isn't type theory only how to map one set to another set? Maybe. I don't know. Fucking type theory. They were talking about here about like the set theory, and it's different, right? Types theory versus the set theory. It's different, right? it behaves differently from the set theory in several important ways. What are these ways? I don't know. Oh, this is what a judgment. Informally, a deductive system is a collection of rules for deriving things called judgments. A good way to think about this is that in set theory, membership is a relation which may or may not hold between two pre-existing objects A and A, while in type theory we cannot talk about an element A in isolation. Every element by its very nature is an element of some type, and that type is generally speaking uniquely determined. Thus, when we say informally, let x be a natural number, in set theory, this is a shorthand for let x be a thing and assume that x is belonging to n. Whereas in type theory, let xn is an atomic statement, which cannot introduce a variable without specifying its type. You see? You see the difference? You understood everything, right? I'll pretend that I understood everything too. Alright, so over here they're talking about capturing the variables, sure. Or whatever. Of course we should all be familiar. This should be familiar to any mathematician. It is the same phenomenon as the fact that if fx is the integral of dt by x minus t, then ft is not this, but rather this. Yes, 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 of course. There, we have seen how to define functions in one variable. They taught us most of the set theory in uni. You know category theory too? Or is category theory different from the set theory? I don't know, I didn't learn any of that. I think. Maybe I did. Category theory and set theory. Hold on, I'm not a bot. Show me. Just a different language or different foundation of mathematics? They're complementary to one another, not in competition. You know, category, just a little bit because of dogshit Haskell. You don't like Haskell? What do you like? What's your language of choice? Haskell for 4 years is a hobby. Why did you stop? 4 years is a lot of years to do Haskell, so I would assume you are you should be pretty good at it. Why don't you like it? Isn't like if you overcome the initial like learning curve, it should be nice to enforce more properties of your program at compile time, I guess. That's the whole point. Right? Lazy evaluation killed it. Yeah, I don't think I'm a fan of lazy evaluation, but I mean it's useful sometimes. I think like having a laziness is useful. Although I'm not sure if it's needed on like the language level. Right? Like I remember when I was trying OCaml has the lazy keyword. So like OCaml by default is not really a lazy language, right? But then you just say like lazy something, and then like all that lazy does technically is just like making like a function that will only be evaluated once. Like it can be done as a library, can it not? I'm not sure. I think sometimes laziness is nice, especially when you are doing some configuration. So like I'm using Nix, right? And the Nix is a lazy language, and the fact that it's lazy is making some of the things like really nice when you use it for configuration. A camel does functional programming right. All right, so you like OCaml more than Haskell. All right. The things that I didn't like about OCaml, though, was the absence of type classes compared to Haskell. You think doing it right is the module system from OCaml is more right than the type classes? I don't think OCaml does like I don't know what is the definition of the functional programming though. I think if like from the mathematical point of view, Haskell is closer to the like correct definition of a functional programming, where the function has like an argument and then it returns the result and it cannot access anything else. And there is no side effects. You have zero prediction of performance. Debugger is necessary for anything more complex, and because everything is lazy evaluated, the debugger is jumping all over the place. Yeah, that was also like that was the reason why I never got into Haskell. So like I was trying to make games, and I thought like that the language is really nice, but it was really difficult for me to like get an understanding of like how the performance characteristics of the programs that I write. And if you want to write something that is performance, you basically write it completely different than normal Haskell. It becomes like a different language. This is hot. Have you read Hot, Nerdzel? You like Haskell's type classes more, and I would wish OCaml to adopt it instead of its module functor system, but we can't have everything, right? Well, I mean, I think that we should have both. So like yeah. Wait, so what do you like? I mean, so there is laziness. Sure. I can agree with you that laziness makes it weird. If not laziness, is anything else that you don't like in Haskell? Though I don't like some of the some of the basic things, like the way they're doing the records, but otherwise Haskell is great. All right, so I guess we agree on that. Are we hating Haskell again? I guess we didn't hate it too much. We just hated a little bit of the fact that the lazy language makes it difficult to reason about what's going to actually happen. It's in a snippet of it. All right. I didn't read anything yet, but we are soon. So like I'm right now at the function types. Soon there's going to be the dependent function types. And then universes as families. Maybe I can skip some of that. Nothing. I don't know. Maybe I will be skipping, and then if I don't understand something, I will try going back. Universes and families. So like I know what a universe is. So a universe is basically a type of a type. That's it. Let's see what they talk about here. So far we've been using the expression A is a type informally. We're going to make this more precise by introducing universe. A universe is a type whose elements are types. Yeah, so basically it's a type of a type. As in naive set theory, we might wish for a universe of all types U, infinity, including itself, that is with U infinity. Yeah. So a type that includes itself inside. That is so a type which is the element of itself. However, as in set theory, this is unsound. All right. What does unsound actually mean? I hear this word a lot, but just not safe. But like, what does it mean? Not like we don't have a reliable like proof or what evidence. What does it mean? It means bad. All right. For example, we can deduce from it that every type, including the empty type, representing the proposition false, is inhabited. For instance, using the a representation of sets as trees, we can directly encode Russell's paradox. To avoid the paradox, we introduce the hierarchy of universes U0, U1, U2, where every universe, UI, is an element of the next universe. What? I mean, I've seen this before. But I still don't understand exactly what this means. Oh, Rinks. It's got a pretty good GC system, easy interrupt with CABI lenses and monad transformers. Solve a lot of problems, but laziness by default just kills me. The universe onion. Yeah. This is unsound. We can deduce from it that every type, including the empty type, represented in the proposition false. Like, what does this even mean? Do you understand this, Nerdsoul? Like, Nerdsoul, you know these fancy words, right? Can you explain this in human language? Is inhabited. So basically, if we have a universe which includes itself, right? Then, if we have the definition like this, then we can prove that a type, so an empty type represents the proposition false. This is like the never type from Rust, or like the void from Haskell, I guess, right? It is inhabited, as in it has elements where it actually should not have elements, right? So like that's what we can prove. Like, how do we prove this? Why am I reading a book about homotopies? I don't know. I just thought I just saw this book being referenced in multiple places when I was like researching things for making a language. So I should probably read it. It's been referenced in a lot of places. You're reading a universe of all types is self-contradictory. Yeah. Yeah, like they say they can deduce it. Can you give me a link? Like, how can we deduce this? For instance, we can using the representation of set as trees, you can directly encode Russell's paradox. I don't know what is Russell's paradox. Can I click on this? Coq 92A theory, Coq the paradox of trees in type theory, BIT numerical mathematics, cited on page 24. So like what, to search for this book, and this is like another book which like describes why this is all wrong. How long is this? That's not long. With some lemmas, Russell. Right. Representation of paradox in type theory. Right, I'm not reading that. No. Let's just ignore this. Whatever this is here. Maybe I can figure it out. See 1.7. No, I mean, this is just the coproduct type, the empty type. They just, I think this is just referencing what is an empty type. It's not referencing like the proof. This over here, though, is probably some proof of why this is bad. Moreover, we assume that our universes are cumulative. That is, all the elements of the ith universe are also elements of the I plus 1st universe. So A is UI, then also A is UI plus 1. This is convenient, but has the slightly unpleasant consequence that elements are no longer have unique types. So this means that like this is subtyping now. Right? Okay. When we say that A is a type, we mean that it inhabits some universe UI. We usually want to avoid mentioning the level I explicitly and just assume that levels can be assigned in a consistent way. Thus, we may write that A is U omitting the level. This way, we can even write U is U, which can be read as U is UI plus 1. Having left the indices implicit. Writing universes in this style is referred to as typical ambiguity. It is convenient, but a bit dangerous since it allows us to write valid-looking proofs that reproduce the paradoxes of self-reference. Steam. Yeah, the bot is not working. If there is any doubt about whether an argument is correct, but I can link it to you, I guess. There we go. This is the Steam. Downtown of our game. If there is any doubt about whether an argument is correct, the way to check it is to try to assign levels consistently to all universes appearing in it. When some universe U is assumed, we may refer to types belonging to U as small types. Okay. So small type is basically the type whose element is not a type. So like something that's not a universe. To model a collection of types varying over a given type A, we use functions B, A into U, whose codomain is a universe. To model a collection of types varying over a given type, we use functions B, A into U. These functions are called families of types or sometimes dependent types. They correspond to families of sets as used in set theory. We use functions BA into U. So basically, this is a function that returns a type because U is a type of a type. So U is a universe. So this means that this is a function returns a type. And B is the argument of this function of type A. And A can be anything. It's not necessarily a type, right? So this is easy. Okay. I understand this. An example of a type family is the family of finite sets n into U, right? Okay, so fin n is a type with exactly n elements. We cannot define the family fin yet. Indeed, we have not even introduced its domain n yet, but we will be able soon. We may denote the elements of fin n by 0, 1, and n minus 1n. We subscript to emphasize that all elements are different from fin n, are different from fin m. Okay, sure, whatever. A more trivial but very important example of a type family is the constant type family at a type B, U, which of course is the constant function lambda x, x of type A, returning B. Which is A into U. Okay, so why do we even have an argument here then? Like it still is a type family, which just ignores the argument. Sure, as a non-example, in our version of type theory, there is no type family. I and UI. The indexed universe. Indeed, there is no universe large enough to be its codomain. There is no type family. This. Yes. So like we cannot have a function that can return any of these universes, right? Because for all the different universes, the types are different, and the type of the result must be not a different thing, right? Although I would guess that if we have a dependent function, that we would be able to do that, no? But then it's not a type family, I guess. Moreover, we don't even identify the indices I of the universes with natural numbers. Okay. Dependent function types, p-types. In type theory, we often use a more general version of the function types called a p-type or dependent function type. The elements of a p-type are functions whose codomain type... Well, like, I hate this word, codomain. Why just... Codomain is the return... Codomain is the return type of a function, right? Okay. So the elements of a dependent function, so like dependent functions are functions whose return type can vary dependent on the argument. That's what this means. Called dependent functions. The name p-type is used because this type can also be regarded as the Cartesian product over a given type. Given a type A U and a family B, A into U, we may construct the type of a dependent function Bx A Bx U. There are many alternative notations for this type, such as... Okay, so what is this? We have a p. P is a p-type. It is a dependent function. It's a dependent function taking x of type A as an argument, and it returns the b, but b depends on x. So we'll need to like invoke the function with the actual value to figure out the concrete result type, right? And we can have alternative notations. I hate the fact that they have many alternative notations. Why not just stick to one? If B is a constant family, then the dependent product type is the ordinary function type. If B is a constant family, then it's the ordinary function type. Yeah, so like if B is a constant, then it doesn't matter what the argument actually is, which makes it a normal function and not a dependent function. Okay, that's easy. Indeed, all the constructions of p-types are generalizations of corresponding constructions of ordinary function types. We can introduce dependent functions by explicit definition. To define function f, where f is the name of the dependent function to be defined, we need an expression phi of type bx, possibly involving the variable x. And we write fx is phi. Alternatively, we can use the lambda abstraction. So like it's literally the same thing as normal functions here. As with non-dependent functions, we can apply a dependent function to an argument A to obtain the element. So if we apply the function f to an argument A, we get as a result something of type B that's dependent on the same argument. The equalities are the same as for the ordinary function type. We have the computation rule. Phi is replaced. Okay, similar, we have the uniqueness principle. As an example, recall from 1.3 that there is a type family thin n into u whose values are the standard finite sets with elements. There is then a dependent function f max, which returns the largest element of each non-empty finite type. So f max n is n plus 1. You cannot find a bug in 100 lines of code. You want me to find a bug for you? I don't know if I will be able to. But if you want, you can share. I can take a look. If I don't find it in 1 minute. Then we can pass it to the next person. What are you writing? Are you working on the language? As was the case for fin itself, we cannot define fmax yet, but we will be able to soon. Another important class of dependent function types which we can define now are functions which are polymorphic over a given universe. A polymorphic function is one which takes a type as one of its arguments, and then acts on elements of that type. An example is the polymorphic identity function ID. Oh, I see. So like you see here, what they are doing is they are saying that polymorphic function is basically just is actually a dependent function. So like wait, does this mean that I have dependent functions already in cast? We define this by ID, which we define by ID is like for all types, we return this. Code generation for polymorphic struct. Some scope is not right. Play cast lang. Let me see here. So here's what they are saying, right? For all x, this is what they are doing. Lambda x or a of u, lambda x a x. If I want to convert this to my cast code, this would be so this is ID, right? They were saying this, right? So like if I try to convert this to my cast code, this would be ID is for all a, which is a type. So like type is the universe for me. This returns a function that takes argument x of type A and returns x, right? That's how we convert this into cast. So the difference is that they treat, so like I'm having these, like I call these templates, right? But they are technically just functions, but there is no distinction between the two in this book. Which removes white space. GG. You're trying to generate hash table string U64. Tracked hash table KV. Length entries array. Struct array. Struct entry. Okay. Now I understand. Wait, is this your language? Is that how it looks like? Yes. What's this? Struct array t length data mode t. This is what my question is. So does this mean that the data is... What is this mut here? Mutable slice. So it's not like in Rust where you would be able to mutate the array. It's more like all the other languages where you have a reference and its mutability is dependent on the type. So you can have multiple shared mutable references. It's a known dynamic array. Like, why do you need this to be specified as mutable, though? Like, if the array is mutable, then this is mutable, no? That's how it's done in Rust. But this looks more like the mutability that is done in, like, OCaml, for example. But you don't say that data is mutable. You say that the slice type is mutable, which is weird to me. I don't know. Just simple permission model. Okay. Sure. Where was I? The ID, the ID function, like lambda abstractions, p's automatically scope over the rest of the expression unless delimited. So this means that, okay, yeah, sure. This convention, though, unusual in mathematics, is common in type theory. Is usize not mutable then? Yeah, I mean, from what I understand, it is mutable. If it was not mutable, it would not be a dynamic array, right? Fields don't have mutability. Yeah, I don't know, like, it's weird that your type has mutability. Like the reason why a reference and a mutable reference are different is because it's a reference, it's not like owning. But when you have a slice, like your struct, your array here is owning this slice anyway, right? So if it's owning this slice, then why do you need the mutability here? It's not any different from the field. Why is it different at all? The only reason for it to be different, I guess, is because your slices are actually pointers. If this is represented as a pointer, which is basically a reference, then that's why you need the mutable keyword here, right? Is that why? So yeah, because this is a pointer, so this technically is a mutable reference to a slice, kind of, in Rust. I mean, because you can, like, share this, right? So like in Rust, you would say something like data is box slice, I guess. This encodes the size of it too, yeah. Same as Rust, but different syntax. Wait, I mean, what is in Rust different syntax? Mute t. Well, that's why it's confusing, I guess, because I thought that in Rust the alternative should be box and a boxed slice. It's not a reference because the array is owning this slice, is it not? Why is it a reference? It's not. It shouldn't be a reference. It should be like an owned pointer, right? Because when you drop the array, it should free this memory. No. But yeah, if you can like share this, then sure. Just basic data type with pointer plus length, known size of 16. Yes, sure. That's how the boxed slice in Rust is represented too, right? But there is no mutable keyword there. Like again, like the alternative in Rust is not a mutable reference to a slice of T. It's a boxed slice, which so I still don't get the mutable keyword. Why do you need it? Because it's not referencing some other slice, right? It's owning the slice. That's the distinction. Hmm? All right. Anyway, I don't know much about your language, so this convention, yeah, this is just how to write this thing. We sometimes write some arguments of a dependent function as subscripts. For instance, we might equivalently define the polymorphic identity function by ID A. X is X. We might equivalently define the polymorphic identity function by ID A. X is X. Moreover, if an argument can be inferred from context, we may omit it altogether. For instance, if A is of type A, then writing ID A is unambiguous, since ID must mean ID A in order for it to be applicable to A. So, okay, what they are saying here is that you can call a polymorphic function by inferring the argument. Sure. Another less trivial example of a polymorphic function is the swap operation that switches the order of the arguments of a current2 function to argument function. So swap is for all A, for all B, for all C, they are all different types. A function that takes a function from A into B into C and returns a function that takes B and A and then returns C. We can define this by swap ABCG is lambda B, lambda A, GAB. Sure. Wait, what? Well, I mean, I understand this, but we might also equivalently write the type arguments as subscripts. Like, what? I like this is my my only problem with this book so far. I think they like all they are doing is they are describing 10 different ways to write the same thing. Why? Why do you want to be able to do this and do you want to be able to do this? Swap ABC are like the type arguments, and then G is the actual argument. Note that we did note that as we did for ordinary function, we use curring to define dependent functions with several arguments as a swap. However, in the dependent case, the second domain may depend on the first one, and the codomain may depend on both. That is, given A, U, and type families B, A, U, and C, for all x, a, b, x into u, we may construct the type. So like basically if we try to do the swap, but these are all dependent functions, not just functions from a to b to c, then like the type of b depends on the type of a, right? That's why it's a type family, not just a type. And c now depends on both a and b. We may construct the type this cxy of functions with two arguments. We're current to define many functions. Hold on. So we may construct the type for all x of a for all y's of type bx. We return cxy. Yeah. Yes. A function. So like this is the actual type. Instead of a into b into c, it's not that simple anymore. This is the alternative of a into b into c, but with dependent types. If in the case when b is constant and equal to a, we may condense the notation and write in the case where b is constant and equal to a, we may condense notation and write p x and y are a. Sure. So yeah, for instance, the type of swap could also be written as for all a and b and c are all types. Then it's this. All right, so this is just like another. Sure, this is just another way to write this. Finally, given f of this type and the arguments a, and b of ba, we have fab is of type cab, which, as before, we write as fab is of type cab. All right. Sure, but we cannot swap this anymore. Yes. Product types. Given types a and b, we introduce the type a x b, which we call the Cartesian product. We also introduce the null array product type called the unit type 1 u. We intend the elements of a type of a x b to be pairs where a is a and b is b, and the only element of 1 to be some particular object 1. All right, so this is like an empty tuple. This is a tuple with 2 elements, a pair. Sure. However, unlike in set theory, we define ordered pairs to be particular sets and then collect them all together into a Cartesian product. In type theory, ordered pairs are primitive concepts, as are functions. All right. Remark: there is a general pattern for introducing a new kind of type in type theory. We have already seen this pattern. So it's worth emphasizing the general form. Specify the type. We specify how to form new types of this kind. Okay. To specify a type, we specify how to form new types of this kind. What do you mean of this kind? We're trying to specify a type, not a kind, aren't we? How to form new types of this kind via formal formation rules. For example, we can form the function type A into B, where A is a type and B is a type. We can form the dependent function type when A is a type and Bx is a type for x of type A. How to construct elements of this type. All right, yeah, because we specify kinds. Yeah, okay, sure. A type is like a sure. How to construct elements of that type. These are called the types constructors or introduction rules. Okay, type constructors, sure. For example, a function type has one constructor, the lambda abstraction. Recall that the direct definition like this can be equivalent to a phrase as a lambda abstraction, lambda x. Sure, so we define, yeah. Sure, how to use the elements of the type. These are called the types eliminators or elimination rules. For example, the function type has one eliminator, namely function application. All right. A computation rule which expresses how eliminator acts on a constructor. For example, for functions, the computation rule states that lambda x phi a is judgmentally equal to the substitution of a for x in phi. Yes. Sure. All right, so these are eliminators, and this is how eliminator actually works. Okay. So this is like the formation rule is like the definition of a type. Construction, like formation rule is like how to write the type, I guess. And then constructors or introduction rules is how to construct elements of that type. So like the definition of the type. How to use elements of the type. So what can you do to this, right? So for example, for a function, you can apply a function, and then how you actually do that, how you actually apply a function if you have the value. All right. An optional uniqueness principle, which expresses uniqueness of maps into or out of that type. For some types, uniqueness principle characterizes maps into the type by stating that every element of the type is uniquely determined by the results of applying eliminators to it, and can be reconstructed from those results by applying a constructor, thus expressing how constructors act or eliminator duly to the computation rule. Expresses uniqueness of maps into or out of that type. For some types, the uniqueness principle characterizes maps. All right, yeah, so it's either a map into or a map out of the type. Okay, so for some types, it's the map into the type, and then for the others, it's out of the type. So if it's into the type, then like the every element of the type is uniquely determined by the results of applying eliminators to it. Every element of the type is uniquely determined. Every element of the type is uniquely determined by the result of applying eliminators to it. Eliminator is what you can do. Yeah, sure. It's going to be reconstructed from those results by applying a constructor. Thus expressing how constructors act on eliminators duly to the computation rule. So it's basically uncompute. So like for a function, this computation rule specifies how to actually apply a function, but the uniqueness principle means that if we have the result of a function, if we have applied the function, we can reconstruct the function that we originally had from the result. Is that it? For example, for functions, the uniqueness principle says that any function f is judgmentally equal to the expanded function any function f is judgmentally equal to the expanded function x fx, and thus is uniquely determined by its values. What? For other types, the uniqueness principle says that every map from that type is uniquely determined by some data. As an example is the coproduct type, whose uniqueness principle is mentioned over there. When the uniqueness principle is not taken as a rule of judgmental equality, is often nevertheless provable as a propositional equality from the other rules of the type. In this case, we call it propositional uniqueness principle. I didn't understand a thing here. Express uniqueness of maps into or out of the type. Uniqueness principle characterizes maps into the type. Maps into the type. By stating that every element of the type is uniquely determined by the results of applying eliminators to it. How to use elements of that type. Results of using the type. Every element is determined by the usage. Applying a constructor. Expressing how constructors act on eliminators. Constructors act on eliminators. Constructing elements of that type is acting on the usage of that type. What? What is it even trying to say? You should stream this content in the evening so we sleep listening to you reading a book, but it depends when where you're from, right? Also, some people like to have naps during the day. You say in the evening, but how many people are actually going to bed in the evening? Isn't like most people now? I know about most, but like, do most people still work like start working in the morning? Most of the like people that I know who work like as software developers, they start working during the day. The morning is when people go to sleep. You sleep at 4 a.m. Yeah, there you go. See, that's like most people that I know how it works. Is it only so although about like software developers? Like other people don't have the flexible schedule or something? I don't know. I know nothing. It's been a while since I was talking to actual people. Did anyone understand what this uniqueness principle? Did anyone else read this book before who is watching the stream right now? Let's ask ChatGPT. I don't understand this. What is uniqueness principle from Hot? Do you know? From Hot. Explain. Like I'm 5. In a super simple, like you're 5 way. Imagine you have a teddy bear. You have one teddy bear. It's soft brown and you love it. Now let's say there is only one teddy bear like this. Now that's uniqueness principle. That's what the uniqueness principle is kind of saying, but with methy things instead of toys. What is a thing in Hot? In Homotopy type theory, we work with types. Think categories of boxes and things, and elements of types, the things inside the boxes. For example, type animal, element cat. Now, sometimes we define special things, like saying this is the only cat that purrs this way. So what's the uniqueness principle? It says if you define something in a very precise way, then there is only one of it. Any other one that matches all your rules must be the same. In Hot terms, it means if something is defined by a universal property, like the thing that does X for all Y, then it's unique up to identity. Which means any two versions of that thing are basically the same. We can travel between them without any trouble. In short, in grown-up terms, the uniqueness principle says if something satisfies the universal property, then it's unique up to homotopy or identity. In 5-year-old terms, if you follow special rules to make something and something else follows the same rules, you both end up with the same thing. So what's the uniqueness principle for a function? Imagine you're drawing a line. Let's say you have 2 crayons and you're told draw a line from dot A to dot B. You do it once with the red crayon and once with the blue crayon. If both lines start at A and end at B and follows the same path, then even you use different crayons, you drew the same line. That's the uniqueness principle. All right, I understand this. Is it possible to summarize what we've been through this book so far? I basically I didn't even read much. We basically read what's a function, what's a universe and type family, and what's a dependent function type. And then inside the product types, which is basically defining what a tuple is, I guess. I mean, you know what a product type is, right? There is this thing which specifies how to specify a type, which includes the uniqueness principle. I am trying to understand what it is. But yeah, not much. We just know what a function is and what is a universe and what is a type family and what is a dependent function. That's it. Suppose we have a function f from a into b. Now imagine someone else has a function g from a into b. If for every input we know that fa is equal to ga, then f and g are the same function. Now, I mean, this is like, yeah, so this is obvious, right? But why do they write it in like look at this here, right? So for example, for functions, the uniqueness principle says that any function f is equal to the expanded function. This is not the same thing as ChatGPT is saying, though. The ChatGPT is saying is that if we have two functions and they are the same, if being applied to any argument, they are the same. They have the same result, right? That's not the same thing. It's uniquely determined by its values. Any function f is judgmentally equal to the expanded function. You cannot see the right side of the book. Dude, I'm just going to hide this then. There we go. There's not much. Can I move this to the left? I guess I can do this. For example, for functions, the uniqueness principle says that any function f is judgmentally equal to the expanded function. Any function f is equal to the expanded function. Lambda x fx. And thus is uniquely determined by... I don't understand. What is this sentence even saying? Right, maybe I'll get it later. Like, we will... I'm guessing that we will see other uniqueness principles in, like... we actually seen this before, right? Uniqueness principle. Right? So we have a uniqueness principle. F is the same. So this is for dependent functions, for example. F is the same as lambda x fx. But how does it prove that anything is unique, though? I mean, sure, it's like a function is the same as a function that takes an argument and applies that function to the argument, right? Because, I mean, yeah, that's what, yeah, sure. But, like, what does it have to do with uniqueness? The same paragraph explains non-function types uniqueness. It does so for the coproduct types, right? For other types, uniqueness principle says that every map from the type is uniquely determined by some data. For example, the coproduct type, the uniqueness principle is mentioned over there, but I have not been there yet, right? 215. Yeah, we have not been there yet. They're just mentioning something from the future. Or is the TTS? I thought that would be TTS. Was this a business movie? Hello, Pigorle. Can I know? I might be a little bit too dumb. I don't understand this book. It means an arrow. Wait, what means an arrow? What's an arrow? What are you saying? This symbol that you use, the fat arrow, is not even used here at all. If delta x is a function and it has method fx, that's equivalent to the function type, the delta x fx means it's not a delta, it's a lambda. This is a lambda, not a delta. Dot means this in JavaScript. Yeah. This is a lambda. So let me show you this. I don't know if you know Rust, for example, right? What this means is that you say that so like we have function f which takes some argument, right, x, and this is so they're saying that f is the same as a lambda. So in Rust, lambda is written like this, fx, for example, right? In JavaScript, it would be x into fx, I guess, right? That's how you do it in JavaScript. Like in Haskell, you do x into fx, I guess. It's all like same thing. Yeah, it's just a lambda closure, whatever, yeah. So they are saying that the uniqueness principle is that the function is the same as like a lambda, which applies the argument to the function, but I don't understand why does it have to do anything with uniqueness. I don't get this at all. Let's just skip this for now. The inference rules in appendix are organized and named accordingly. The way to construct pairs is obvious. Okay, and now we just go for the product type. So product type is just a pair, a tuple with two elements, right? A product A and B. So we have the element A, we have the element B. So here's, here you go. The uniqueness principle for products. What is this? We expect that every element of A and B is a pair, which is the uniqueness principle for products. What does this even mean? Every element of A and B is a pair. We do not assert that this as a rule of type theory, but we will prove it later on a propositional equality. How is a function equivalent to it being called with an argument? No, the function is not equivalent to it being called with an argument. A function is basically equivalent to a closure which calls the function with the closure's argument. Yeah, it's equivalent to the closure, not to the function being applied. Every element of A and B is a pair, which is the uniqueness principle for products. We do not assert this as a rule of type theory, but we will prove this later on in the propositional equality. What does this mean? Uniqueness principle is the most is the only thing that I don't understand so far, I think. Every element of A and B is a pair. But isn't like A and B is a pair? I mean, like, what do you mean? Every element of A and B is an element of A and B? That's what it's saying? The way to construct pairs is obvious. Given A, we may form a pair of A and B, which is an element of A and B. Similarly, there's a unique way to construct elements of 1, namely we have 1. Oh, a star. A star is a type of... Oh, okay, so this is a unit, which in Rust is just an empty tuple, right? And this is the tuple, the unit value. They call it a star, and the type is 1. Sure. They're building up uniqueness principle as a usable abstraction, which can define the identity more formally. Like, I just don't understand what it means. Every element of A and B is a pair. Isn't that literally the definition? Why is it like called the uniqueness principle? It's just the definition, no? The way to construct pair is obvious. Given A and B, we may form a pair. So they are saying that a pair is an element of A and B. But okay, I think I understand. Maybe so like so this is how you create a pair, right? This is how you create a pair. And if you create a pair, it's the type of the pair is this, right? But then they are also saying that if you have something of this type, then you can also represent it as a pair. I think that's what they're saying. You know? So like it's basically like destructuring, like pattern matching kind of thing. So like if we have something of type A and B, then we can like pattern match it. So like it's a pair, you know? I think that's what it means, maybe? It's like the inverse of constructing an element, right? It's like deconstructing. That's what they're saying. The uniqueness is the is basically the inverse of the computational rule, which is how you down. Wait, what is a computational rule? Computational rule is how you do this, yeah. Constructor. A and B are sets. A is an element of A, and B is an element of B. No, that is something that I understand, yes. That's simple. I try to understand what is the uniqueness principle. I've been so obsessed with Noita that I had Twitch open. I didn't notice you online. How's it going? What type of feature are we working on? I'm not working, I'm just researching. I'm trying to read this book. We are currently 10% through. Why am I studying Homotopy type theory? Just so that I don't know, maybe it will help me understand something. I don't know why, just because I can, you know? I saw this book mentioned in a lot of places, so I thought I should figure out what the book is about. Uniqueness of maps. In or out of the type. Uniqueness of maps. Dually to the computation rule. Oh, eliminator, okay. Alright, how can we use... Now, how can we use pairs? How can we define functions out of a product type? How can we use pairs, which is how can we define functions out of a product type? Alright, so like, the function can be used by applying the function to the argument. How can we use a pair? Let's consider the definition of a non-dependent function f a into b, a and b into c. Since we intend to the only elements of a and b to be pairs, we expect to be able to define such a function by prescribing the result when f is applied to a pair. What's prescribing? State authoritatively. We introduce a new rule, the elimination rule for products, which says that for any such g, we can define a function f, a and b into c. So a function f ab is gab. We avoid writing gab here in order to emphasize that g is not a function on a product. So basically, if we have a product, then how do we get rid of a product type, right? How do we get rid of a tuple? And they specify that in order to get rid of it, we need to have some function that operates on two arguments, and we apply that function to those two arguments, right? Yeah. So in order to get rid of a tuple, we need a function that takes both things, right? I guess is what it means. Yes. Has this helped you learn math syntax? I mean, most of this, like, I knew what the product type is before, right? The arrow. I don't know. So far, the only new syntax is like this, the P, I guess, which is the dependent type the dependent function. So this is a normal function and this is a dependent function, but I don't know. And then there's like 10 different ways to write this. Egbert Rijks. I don't know. Is it the book by Egbert Rijks, maybe? Or is the authors? I thought this is like the book is open source, so it's like not by a single person. These are the people who were official participants. Egbert Trike is there. Yeah. Product types. All right. So you know this, you understand all of this, right? Can you explain this like to a person who never read anything? His book is intro of what? Wait, the intro, like the first things, this introduction, or just a different book? Should I read some intro to understand what is being written here easier? Do you understand what is a uniqueness principle? Because I don't get it. Introduction to hot. All right. Introduction to hot. This thing. This is an introductory book to a univalent mathematics and homotopy type theory. The book is entirely self-contained, in particular no prior familiarity is assumed. Okay, so like this book that I'm reading is assuming some familiarity, but this book is not assuming anything, right? Should I just read this instead then? Dependent type theory. Dependent type theory, judgment, contexts. Mathematical argument or construction consists of a sequence of deductive steps, each one using infinitely many premises in order to get to the next stage in the proof or construction. Such steps can be represented by inference rules. Should I start with the introduction? This book started as a set of lecture notes at the Carnegie Mellon University in 2018. Homotopy type. Oh wait, this is a recent one, right? 2018, they said. Following the discovery of the homotopy interpretation of Martin Love dependent type theory by in dependent type theory, there are primitive objects called types and primitive objects called elements. Martin dependent type theory contains type formation rules for many operations that we are familiar with from traditional mathematics. Product sums the inductive types. There's the type of natural numbers. It's called dependent type theory because both types and elements may be parameterized by the elements of other types. An example of dependent type because it's parameterized by two elements. This the identity type IDA AB is an example of dependent type because it's parameterized by two elements A and B of type A. The elements of the identity type are called identifications. And the type theoretical way to assert that A and B are equal elements of type A is to assert that there is an element in the identity type. Hold on. Maybe I skipped too much. Oh wait, this is the introduction. What? I know what a dependent type is. That's not difficult. But the language that you're using here, like, what is this trying to say? Identity type. IDA. So this is the identity type. Why does it have two? What is this? What does this even mean? I need a function A into A. Why is there a B then? Why is there a B? If this is an A into A, it's a type, not a function. I know what an identity function is. This is an identity type. It's an arrow. I don't see any arrows here. This is an example of a dependent type because it's parameterized by two elements, A and B, of type A. The elements of the identity type are called identifications. A type that depends on A and B. Why is the identity type depends on A and B? What? I don't get it. The identity type, like what? The identity type. What is the identity type? Is the type of the identity function or what? So the type of the function that takes A and returns A is dependent on the type of the argument. Sure, but why is there a B? Right? So like the same example from this book, which I read through this already, right? There was the identity function here. Here's dependent function type, right? And then they specify the they show the identity, right? I think. Down. There you go. This is the identity type. So this is the A is a type, right? The type of A is a universe. And then we have A into A. Where's the B? There is no B here, right? Why is there a B here? This makes no sense. Functions in HOT are morphisms. You're just making it worse. That's not helping me to understand anything. This is the worst introduction ever. Read the following lines. Why don't they swap the lines then if I need to read the following thing first? Okay, sure. This is an example of dependent function. The elements of the identity type are called identifications. And the type theoretical way to assert that A and B are equal elements of type A is to assert that there is an element in the identity type the type theoretical way to assert that A and B are equal elements of type A is to assert that there is an element in the identity type. Alright, sure. In other words, to prove in type theory that two elements A and B in type A are equal, one has to define an identification B. ID A and B. It is therefore common to write A is equal to B for the identity type ID A, AB, or if we want to be explicit about the ambient type, we can write ID equal AB. Are you sure that this is easier? The rules for the identity type postulate that this is inductively generated by one single element. Like, I mean, I think I understand what this is trying to say, but I don't know. I don't know. I hate the way they write it. Not really understandable easily. There can be multiple types of identity, not always equality. There's structural equality, there's value equality, there's type equality. Sure. 1, 2, 3 is equal to 1, 2 because both are arrays. The equality function is not doing value equality. All right. I mean, we are trying to see if two values are the same. Or in order to do that, we need to have a proof that they are the same. In order to have the proof, we need to define this thing, right? So like if I have the P of type, of the identity type, for these two, then we know that these two are the same thing, because this type is inhabited. We prove that it's inhabited by constructing a value of this type, right? Like something like that, but like it's like, I don't know. Because this was written by Homotopy folks way before computer science people. Yeah, is there like a version of this book for programmers? You know, not for mathematicians. This is my biggest problem with these things, the language they use. Rules of identity postulate that it's inductively generated by a single element. Right, let's just try following this. The rules for identity type postulate that it is inductively generated by one single element. Raffle A is AA. So basically A is equal to A, right? This raises an important question. Since the identity type is a type... Wait, what is this again? It is therefore common to write A is equal to B for the identity type. So like A is equal to B is just another way to write this type, right? Or something. So ref A is of this identity type. What's the value of this ref A? The amount of times developers run away from math just to come back to it after 10 years is amazing. Raffle is a proof, it is condition. Well, I mean, for this specific thing, it's not really like a proof. I guess this is more like an axiom, because like A is equal to A. Like, do we actually prove it? How do you prove that A is equal to A? I guess like for other for like the other things, you would need to actually provide the proof, right? It's an axiom, it has no proof, and it's assumed to be trivially correct. Yeah, that's what I said, right? But basically, yeah, sure. Since the identity type is a type, it could be possible that there are many identifications. B is A is B. Yes, so we can have multiple proofs that A is equal to B, right? That's what this says, right? We can have multiple proofs that A is equal to B potentially. On the other hand, the identity type is generated inductively by only one element, reflexivity. Is it possible to prove using the rules of the identity type that there is indeed and at most one identification? The pioneers of type theory have already been aware that this seemed impossible, but not until these guys constructed a groupoid model. And maybe I don't need the introduction. Can we just skip the introduction? What I like more about like this actual book compared to this introduction is that like this book actually like introduces all the mathematical notations for me, right? Like over here you see that they are using A is equal U B. Okay, okay, this has been introduced, right? But what does this symbol mean, right? I have no idea. Have they introduced this symbol before? I don't think so. Like even over here when they specify the identity type, they don't say what this notation actually means. But this book does. Some of this notation is assumed knowledge. Yeah, but like that's what I'm saying. This book is called Introduction to Hot, and this book is the actual Hot, right? But this book that is not the introduction is introducing the things that are assumed to be known in the introduction, right? There is no link to the appendix here. All right, we have something here, the index. Going to search for it. I don't even see this. No, it's over here. This is equivalence. This is equivalence. See equivalence. How do I see equivalence? Can I see the equivalence, please? Where's the link? There's no link. Why am I reading this? I don't know. Just to see if I can understand anything. Page 113. Oh. But why is the link over here instead of here? 342 property. What? 113. I think I'm gonna try to continue with this book maybe, but I'll keep this one in mind. Maybe I will read this one too. Maybe I'll read some of it off stream if I don't get far today. But I mean, function types is easy. Universes family is easy. Dependent function types easy. Product type itself is easy. The only thing that I don't understand so far is the is what the uniqueness principle is, I think. No objective, no goal. Well, yeah, I am making a language. Yes. I guess I kind of want dependent types to be there. And maybe there is something else that I should I'm just trying to like look into what I want potentially. I guess. Down. Um. As far as I understand, like for dependent types, you would need to provide the proof. So maybe like this and uniqueness principle is going to be like used like for proving certain things, right? Shuba might be getting frustrated. They seem to be familiar with the subject. Yeah, it's frustrating to see someone who doesn't understand. And you understand it. Right. I'm just trying to see where was I. Over here, I think. Yeah. So they were saying that in order to use a product type, we need to have a function that uses two things. Know that in set theory, we would just satisfy the above definition of f by the fact that every element of A and B is an ordered pair. So it suffices to define f on such pairs. By contrast, the type theory reverses the situation. We assume that a function on AXB is well defined as soon as we specify its values on pairs. And from this, or more precisely from its more general version of dependent functions below, we will be able to prove that every element of A and B is a pair. From a category theoretic perspective, we can say that we define the product A and B to be left adjoint to the exponential D into C, which we have already introduced. As an example, we can derive projection functions. We have projection 1, which takes a pair and returns the first element. We take... I guess like I shouldn't say that this is a pair, right? Because the product type and the pair, they are saying that they are using it differently. A pair is more like the constructor for a product type, right? Is that what this means? So this is the first, and this is the second thing with the defining equations. This is A, this is B, sure. This is a more dev-friendly. Actually, univalent foundations of mathematics with Agda. MLTT in Agda. I'll keep this open too. Is Agda like the proof assistant? Agda, what is this? It's a programming language, dependently typed functional programming language developed for this. Not exactly a proof assistant, right? Agda is also a proof assistant based on the propositions as types paradigm. But unlike Coq, has no separate tactics language. Proofs are written in a functional programming style. We can derive projections. Rather than invoking this principle of function definition every time we want to define a function, an alternative approach is to invoke it once. Rather than invoking this principle, a function definition every time we want to define a function, an alternative approach is to invoke it once in a universal case, and then simply apply the resulting function in all other cases. That is, we may define a function of type rec AB. So this means this is a dependent function. We have C. ABC. So basically, yeah, if we have a function from ABC, we can get AB into C. We define an equation. C, G, AB is GAB, sure. That instead of defining functions such as PR1 and PR2 directly, by defining an equation, we could define this. So the first argument here is the result type, which is A. And this is the implementation. So we have the first element, the second element, we'll ignore the second element, we'll return the first one, sure. I don't know how this helps anything. I can read this though. What is the correct way to learn this material? Is it done into a newcomer? Start with the math? What exactly is the math? There is like so many things, right? I mean, I can understand most of it so far. Here. We refer to the function AB as the recursor. I mean, I'm not sure where we're getting to though. We refer to the function recB as the recursor for product types. The name recursor is a bit unfortunate here, since no recursion is taking place. So even they admit themselves that the naming that they choose is bad. It comes from the fact that product types are a degenerate example of a general framework for inductive types. And for types such as natural numbers, the recursor will actually be recursive. We may also speak of the recursion principle for Cartesian products, meaning the fact that we can define a function from the product into some C as above by giving its value on pairs. So this is the recursion principle. We leave it as a simple exercise to show that the recursor can be derived from the projections and vice versa. We also have a recursor for the unit type. Recursor for the unit. Okay. So we give it a constant. Okay. We define an equation. Math notations jargon is what makes it harder to understand, yes. I think I agree with that. I think that's the issue. The actual concepts are not that difficult once I understand what it's trying to say, but it's just saying it is in a language which is difficult. There is I don't know. Math prerequisites is all probably just set theory, predicate logic, abstract algebra, topology, category theory, etc. Yeah, maybe. So if I don't know category theory, I shouldn't be getting into this. Down. Although we included it to maintain the pattern of type definitions, the recursor for one is completely useless because we could have defined such a function directly by simply ignoring the argument of type 1. Yes. To be able to define dependent functions over the product type, we have to generalize the recursor. Given C, AB into U, we may define a function f, dependent function x, AB, Cx, by providing a function g sure. X, A, Y, B. Okay. And then later they will have the dependent pair, and this Y is going to be BX instead. For example, in this way we can prove the propositional uniqueness principle, which says that every element of A and B is equal to pair. For example, in this way we can prove the propositional uniqueness principle, which says that every element of A and B is equal to a pair. So here's the uniqueness principle for the products, right? For all x, so if we have, so basically, if we have an x, which is a product this is a type. This is a type. And this is like this identity type, which I saw in this introduction book. I don't think I even saw this notation being used in this book before. So this is a proof so uniqueness principle is basically a proof that there exists a pair. So yeah, that a pair is the same as X. How do I know this from another book, like this notation? I don't get it. This is the first thing that they say in the introduction. This is the notation for like the identity type or something, right? Was this introduced here earlier? Identity type. Here we're using it's literally like the next line. Okay, here we're using the identity type, which we're going to introduce below. Okay, of course. How about they don't use the notation that is not like... why are they writing this book in such a way where like I'm trying to just read it top to bottom, but that's basically not the way to read the book apparently, right? they show me something, and they're saying, oh, we were using this thing here, which we did not define yet. So just hold on. Read it bottom top. Is that how you're supposed to read it? Sure. I mean, in this case, it's not very far away, at least. It's literally the next line. Here we're using the identity type, which we're going to introduce below. However, all we need to know now is that there is a reflexivity element of this type for any XA. Given this, we can define uniqueness principle, which is Raffle AB. Hold on, there is a reflexivity element. So X is equal to X. But this is AB. This is a different type, isn't it? Raffle AB. This construction works because in this case, X is AB. Yes. We can calculate. Oh, so we're just calculating that PR1X is actually A and PR2X is B. So we basically calculate this, and this becomes just A and B, and X is A and B. And since the left right and the right side is the same thing, using the reflexivity element, we basically have the proof already, right? Okay, sure. Well typed says both sides of the equality are judgmentally equal. More generally, the ability to define dependent function in this way means that to prove a property for all elements of a product, it is enough to prove it for its canonical elements, the ordered pairs. When we come to inductive types, such as natural numbers, the analogous property will be the ability to write proofs by induction. Thus, if we do as we did above and apply this principle once in the universal case, we call the resulting function induction for product types. Given A and B, we have induction AB is. So if we have a C, which is a function from AB into U is a type, by the way. Town. So induction principle, we get as a result CX. E. So this is like how we construct a dependent function. For products without knowing what a product is, right? We need to supply the dependent function that takes like two separate arguments, not in the form of a product. Sure. No, this is understandable, I think. If you can't explain something to a 5-year-old, you should be allowed to teach it. Well, I mean, it does make sense that like certain knowledge requires some prior knowledge, right? So not everything like can be explained without explaining the requirements. With the defining equation. With the defining equation, induction CGAB is GAB, sure. Similarly, we may speak of a dependent function defined on pairs being obtained in the induction principle. We may speak of a dependent function defined on pairs being obtained in the induction principle. It's easy to see that the recursor is just a special case of induction. All right, what is a recursor again? Recursor okay, yeah, recursor is just a thing that is not a dependent thing, right? Yeah. So induction principle gives me a dependent function as a result. This gives me a normal function from the product into C. But in the induction principle, the difference is that this is the dependent function that we get as a result, sure. Because induction describes how to use an element of the product type, induction is also called the dependent eliminator, and recursion the non-dependent eliminator. Induction for the unit turns out to be more useful than the recursor. So induction principle for the unit, if we have C star I think it's closer to the truth to say that if you can explain it, then it shows that you must understand it. Yeah. You explain induction. What is it inducing? Well, I don't know what is it useful for, but we are trying. So what we're trying to have is this thing on the right, basically. So like we define what a pair is, right? Like imagine if we have a language that doesn't even have pairs at all, right? Like product type is a pair, right? A tuple with two elements, whatever, right? So we need to somehow be able to produce this thing. This thing is a dependent function that depends on the value of our type, right? So in this case, the type is the is a pair, right? So in order to have this, since we like don't, since this is our type, like we need to be able to construct this using something that is not using the type that we are defining, right? Something like that. So in order to have a function that depends on a pair, we need to have a function that takes two arguments separately, right? So if we have a function that takes two arguments, then we can have a function that takes a pair. Not sure what is it used for yet. There's also like the difference between like, so I'm saying pair or tuple, right? So when we work in programming language, we just say it like a tuple, I guess, right? This is the simple tuple, the most simple tuple that is like useful for things, right? It is a pair, right? A tuple with two elements. They call it a product type because that's like what makes sense in math, right? As far as I understand, though, they have a distinction between like actually like when they say product type, it's like the type, but a pair is actually a constructor of that type. I think that's the difference. So that's why they say that we need to like prove that every element of a product type is a pair, and every yeah. That's why we like need to be proving that, right? Using the so yeah, that's what the induction principle is actually being used for, right? We are using it to prove that every element of the product type is a pair, right? A pair is a type, no? Well, I mean, I think in this book specifically, the terminology is that a pair is not a type. A pair is a constructor for the type, which is called a product type. Can you have the link to the book? Sure. Yeah, pair is a pair. It's not like a value; it's a constructor. I'm not sure if a constructor and a value is like the same thing. They never call things values, right? They call them elements, right? So we have a type. A type is basically a set of potential elements, which like when we are programming, we call the sets the types, and the elements we call them values, right? What is a constructor? A value, a type? A constructor is basically a way to construct an element, you know? It is a way to construct a value. Right? Maybe like the product types and pairs are not like the best example here. Maybe the coproduct types. I think coproduct types is the sum types, right? The algebraic data types, whatever. The disjoint union, yeah. I think maybe will make more sense there. Like, you know, when you have in Rust in enum, right? And you have multiple variants. So like every variant is basically a constructor. That's like when you're writing something like Haskell, they are literally just called constructors, right? Because Haskell is closer to math, so they use the same terminology, I guess. So in case of a product, the pair is a constructor. So a constructor is like a way to write, right? Like the product type has only one constructor, right? And it's called a pair. I think that's what's happening here. So I think this will make more sense in the next section. The pair AB is of type AXB. Are the individual A and B of type A or of type B? Or is one of type A and one of type B? Well, A is of type A and B is of type B. Right? We can see this higher up. here, right? So this is how we define a type, right? This is literally what we're trying to do here. We're trying to define what is a product type, right? So in order to define a type, we need to know the construction, the constructor. So for a product type, the constructor is like the pair. Where we have it. The way to construct pairs is obvious. Given A of type A and B of type B, we may form A and B of type A and B, right? That's the thing. A is of type A, B is of type B. Well, I mean, technically the product type is something that you learn in school. I guess, kind of, right? I do remember something. About that. Down. Be able to define a dependent. Right, so this is the induction principle. That, yeah. And then we have the dependent pair types. Sigma types. So the dependent pair type is a similar thing to a product type, but the second element depends on the value of the first element. Right? Given a type A and a type family B, the dependent pair type is written as sigma XA BX. Alternative notations are sigma XABX, sigma with this being underneath, and sigma this with a comma, sure. So the product type is just the AND operation between two types. Well, I mean, what is the AND operation? It's a product operation, like it's multiplication, right? If types is a set, if you have set A and you have set B, so product type is a set where we have every combination of a value from the first set and the second set. That's why it's called the product type. Yeah, close the sidebar, yeah. Sometimes there is not universal agreement on how to pronounce this kind of symbol. Sometimes X is pronounced by. Yeah. A by B. Yeah, because it's multiplication, right? Like 2 by 2. Right, dependent pair like is like I knew what it is before. Like other binding constructs such as lambda extraction and the p's, sigmas automatically scope over the rest of the expression unless delimited. Sure. So like so you see how this book is nice. They actually like specify what is the syntax here for me reading the book in the future. Most of the time they do it before using this syntax. The way to construct elements of a dependent pair type is by pairing. We have A and B as this, given A is of type A and B is a BA. So yeah, basically the only difference between a product type and a dependent pair is that the A is still just A, right? But the B has the type that depends on the value of the first element. That's the difference. And if b is a constant, so like the function does not use its argument, then the dependent pair is just the normal product type. That makes sense. All the constructions of sigma types arise from straightforward generalization. I think it's better to think of it logically as n and or for some or product types. Yeah, I guess I don't like the naming sum type and product type, sure. Although I don't like the way that Rust calls it an enum either. I think the best names for this are like variant types, choice types, something like that. Mm-hmm. It depends on the value, not the type. Yeah, it depends on the value. So one thing that is interesting, for example, about these dependent pair types, as far as I understand, we can define normal like enums. Isn't it union? No, it's not union. It still is a tuple. Like, you know, you have a type like int32 and int32, right? That's just a normal tuple, right? But let's say that you have the second element, which is not just an int, but like like, you know, if you have an array of length n, you know, like a fixed sized array. So if you can have a tuple where this is a fixed sized array dependent on the first element, you know, like this is something that you cannot do in Rust directly, right? So you would be able to do something like struct, like, you know, fixed sized array, where like the size of the array is usize, and then the actual array is like and the size is self.size, something like this, you know. That's something that you cannot do. Oh, enum is a union. This is type of a type. Mm-hmm. Generics are a thing, though. Yeah, but this is not a constant, right? This is not known yet. It's not really a constant. That's the difference, right? So the thing about the dependent pairs, as I understand, is you can actually model the enums. So like, let's say you have an enum foo, which is like, you know, A, I32, and you have like B, which has string inside, I don't know, let's say F64, right? So you have this enum in Rust. If you had a dependently typed language, so like, how is an enum actually represented in memory in Rust, right? It's not exactly a union. So struct foo is actually something that has a discriminant. That's what they call it in Rust, right? Some integer, and then the actual value is a union of those two things. It's either an I32 or an F64, right? That's the actual, like, how it's implemented in Rust. So you can do this if you have dependent types where you have like struct foo, where you have like discriminant, which is like let's say, I don't know, it's probably not an I32, but basically the value is something where the type depends on the value of the discriminant, right? So the type of the value depends on this, right? So you say something like, if discriminant is equal to 0, then the type is I32, else the type is F64. Something like this is how you can implement the enums if you have like the dependent types instead. and then it's more explicit, the actual implementation here, which is kind of cool. I'm not sure if you can like if you when right now in cast these types, the variant types are baked into the language, but it basically can be like a syntactic sugar for this, I think. Maybe. Like, you don't need to support the algebraic data types directly if you have dependent types. In this book, they do have the coproduct types later, so I don't know. But maybe they define, like, maybe that's why they are defining the dependent pairs before coproduct types. Maybe that's why. Mm -hmm. The way to construct elements of dependent pair type is by pairing. We have this, sure, yeah. All the constructions of sigma types arise as straightforward generalizations of the ones for product types with dependent functions, often replacing non-dependent ones. Sure. For instance, the recursion principle says that to define a non-dependent function out of a sigma type, we provide a function g, and then we can define f, which is the recursion principle. So recursion principle is a way to construct a non-dependent function out of a sigma type. Induction principle is a way to define a dependent function. So we can skip directly to the induction principle because it's more powerful anyway. I looked at reachability types. No. I don't think I ever heard about this. Polymorphic reachability types. Tracking aliasing and separation. Tracking freshness, aliasing, and separation in higher order generic programs. Aliasing. Higher order functional programs. What is this? Ownership type system? This is like about the borrow checker? This is like a new, better way to do the borrow checker? We present several case studies as extension, including applications of two capabilities for algebraic effects, one-shot continuations, and safe parallelization. Ownership type system based on the idea of enforcing unique access path has been primarily focused on objects and top-level classes. However, existing models do not as readily reflect the finer aspects of nested lexical scopes capturing or in escaping closures in higher-order functional programming patterns, which are increasingly adopted in mainstream object-oriented languages. We present a new type system, lambda star, which enables expressive ownership-style reasoning across higher-order functions. It tracks sharing and separation through reachability sets and layers additional mechanisms for successfully enforcing uniqueness on top of it. Flow-sensitive effect system, which enables flavors of move semantics and ownership transitive. They're talking about Rust there? I don't know. I guess it's not exactly about Rust. I have a flow-sensitive effect system, whatever that means. Right, that's interesting. I'll take a look at some point. For instance, we can define the first projection from a sigma type. First projection is getting the first element of a tuple of the pair. So the type of it is a sigma type, XABX. That's the, yeah, sure. I kind of like this, like for the dependent pairs. So they have different notations, right? I think this notation for a pair makes more sense to me because they have a comma here. The first element is X of type A. So basically it's, yeah, that's literally how I wrote this. Over here, I guess, right? So you have the first element, which is X of type A, and the second element, we don't name it, we just know that the type of the second element is B applied with X. So projection is a way to get the first element. We just do this. You can watch this to understand the reachability types. 2024. That's a new thing. Just 18 minutes. I'm wondering how, like, the so like they said reachability types, tracking aliasing and stuff, right? So like this is all about aliasing. I've been reading a little bit about like the linear types. Linear types, they don't really allow like aliasing though, I guess. So they're like a simpler concept, but helps with like ownerships too. Find this, let's see. Need function. Oh, yeah, there we go. So like in order to get the first element, we say that in order to get the first element, we just return the first element, right? However, since the type of the second component of a pair is BA, the second projection must be a dependent function. Yeah, because like these, the type of this depends on the value of the first one. So this is a dependent function where we have this type. So the type of this, this is just the type of a function that gets the second element. Yes. And thus we need the induction principle for sigma types, the dependent eliminator. This says that to construct a dependent function out of a sigma type into a family C, we need a function G. Yes. Then we can derive a function yes, C is this. B is the dependent pair. So this function is that. As far as I understand, it allows you how to control how restrictive you want to have your types. Not a single owner like in Rust. Oh, it's not a single owner. All right. I mean, I have this opened. I'm not going to look into it right now, though. Applying this with CP. is B. Applying this with CP is B here 1P. Okay, yeah, so like this is the induction principle, right? But if I apply the induction principle with C being equal to basically the type of the second element of our dependent type, because that's what we need to get the second element, right? With obvious equation, AB equals B. Yes. To convince ourselves that this is correct, we note that B Yes, to convince ourselves that this is correct, we note that B here 1 AB is equal to BA. Yes. This needs to be proven, right? Using the defining equation for PR1. Using the defining equation for PR1. Yes. So like we just yes, okay. Sure. So we use this to prove that this is well typed, basically. Okay. We can package the recursion and induction principle into the recursor. We can package the recursion and induction principles into the recursor. Wait, what? Isn't the recursor the recursion principle? I thought this is the same thing. Wait, what is the recursor? A recursion principle is a way to construct a non-dependent function, right? An induction principle is a way to provide the dependent. Okay. Okay. I mean, these are the principle and the recursor itself. So the recursor for this type is, so like if I are trying to get C from our thing, we need to have a function like that. Sure, and this is the induction operator. Okay, I mean, okay, sure, whatever. I thought this is like the same names, but yeah, so the recursor is the thing that implements the recursion principle or something. Induction operator is the thing that implements the induction principle. Whatever. The defining equation, yeah, sure. As before, the recursor as the special case for induction where the family C is constant. Yes. As a further example, consider the following principle where A and B are types and R is A, B, U. AC. Why do they call it AC? Sure. So we have this. RXY. So this is a dependent pair. Where the second element is depending on the first element, but also like on the outer argument of type A. Sure. And we have this function that returns sigma type, where f is a function from A to B. And then we have the x of A. Rx and fx. Sure. I mean, what are we trying even to do here? We may regard R as a proof-relevant relation between A and B, with RAB the type of witnesses for relatedness of A and B. The AC says intuitively that if we have a dependent function G assigning to every a dependent pair BR, where B is B and R is... You see what's the issue with this here? So they say assigning to every A of type A, right? I read this, they say XA. Why don't they use like the same naming in the description and in the actual formula? They say here X of type A, but it's actually A of type A. This makes it a little confusing to read. We have a dependent function G assigning to every A dependent pair BR, where R is RAB. Then we have a function F then we have a function F of A and B and a dependent function assigning to every A type A witness that RAFA. Our intuition tells us that we can just split up the values of G into their components. Okay, so if we have a function like this, then I somehow already have a function from A into B. Let me think about this. Oh, yeah, we do. Yeah. Okay. We do, because like this is a function that takes A and returns B, right? But also it's a function that takes A and also returns this thing. Yes. Okay, this actually makes sense. What is this used for? We can split up the values of G into their components. Indeed, the projection we have just defined. We can define AC. G is lambda x PR1GX and lambda x PR2GX. Yeah, that's literally what it is. The first and the second element. If we have a function G, right? So verify that this is well typed. Know that if we do this, note that if G is that over here, then we have this of type A into B. Right? because g is a function that takes a as an argument over here, right? So we know that x is an a, and then the result of g is this pair where the first type is b. So this is b, yes. Sure. Moreover, the type p xa rx pr1 gx is the result of applying the type family lambda f being summed over in the codomain of AC to the function. Thus we have that. If we read P as for all and sigmas as there exists, then the type of the function AC expresses right. Have them both on the screen at the same time. So if for all x of type A, there is a B of type B such that Rxy, then there is a function f from A to B such that for all x of type A, this. Yeah. Since this sounds like a version of axiom of choice. So this is the axiom of choice, that's why they called it AC. Alright, what is the axiom of choice? Is that something like... Is that something that I know? It's from the set theory. I don't think I... From the put, the axiom of choice said that any given collection of non-empty sets, it's possible to construct a new set. That given any collection of non-empty sets, it's possible to construct a new set by choosing one element from each set. What? Oh, no, non-empty sets, okay. A new set by choosing one element. Sure. Okay, sure, the axiom of choice. I don't think I learned that one before. The function AC has traditionally been called the type-theoretic axiom of choice. As we have just shown, it can be proved directly from the rules of type theory rather than having to be taken as an axiom. So the axiom is not an axiom, we can prove it. However, note that no choice is actually involved, since the choices have already been given to us in the premise. All we have to do is to take it apart into two functions, one representing the choice and the other one its correctness. Dependent pair types are often used to define types of mathematical structures, which commonly consist of several dependent pieces of data. Take a sample example. Suppose we want to define a magma to be a type A together with a binary operator M, AAA. The precise meaning of the phrase together with and the synonymous equipped with is that a magma is a pair AM consisting of a type and the operator. Since the type of the second component M of this pair depend on the first argument, such pairs belong to the dependent pair type. Thus, the definition of a magma is a type A together with a binary operator should be read as defining the type of magmas to be this. Magma is this. Given a magma, we extract the underlying type. its carrier with the first projection and its operation with the second projection. Of course, the structures built from more than two pieces of data require iterated pair types, which may be only partially dependent. For instance, the type of pointed magmas AM, is equipped with a base point E. Pointed magma is this and AI, sure. We generally also want to impose axioms on such structures to make a pointed magma into a monoid or a group. This can also be done with sigma types. In the rest of the book, we will sometimes make definitions of this sort explicit, but eventually we trust the reader to translate them from English into sigma types. We also generally follow the common mathematical practice of using the same letter for a structure of this sort and its carrier, which amounts to leaving the appropriate projection function implicit in the notation. That is, we will speak of a magma A with its operation M. Now that the canonical elements of pointed magma are of the form A, ME, where A, U, and M this, and EA, sure. This is the frequency with which iterated sigma types of this sort arise. We use the usual notation for ordered triples, quadruples, and so on to stand for nested pairs, possibly dependent, associated to the right. That is, we have X, Y, Z is X, Y, and Z. Okay, sure, yeah. Yeah, that makes sense. Sure. Coproduct types. Given A and B, which are both types, we can introduce their coproduct type, A plus B, so the sum type. This corresponds to the disjoint union set theory, and we may also use that name for it. In type theory, as was the case with functions and products, the coproduct must be a fundamental construction since there is no previously given notion of union of types. In type theory, the coproduct must be a fundamental construction, since there is no previously given notion for union of types. We also introduce another version, the empty type, 0, U. So 0 is the never type. There are two ways to construct elements of A plus B, either by creating the left or the right. In L. Why is it in? What's the in? Injection, of course. Nice choice of words. Either left or right. There are no ways to construct elements of the empty type. To construct a non-dependent function f, a plus b into c, we need two functions, from a into c and from b into c. Then the f is defined with the following equations, sure. That is, function f is defined by case analysis. As before, we can derive the recursor. All right. We can always construct a function f, 0 into c, without having to give any defining equations, because there are no elements of 0 on which to define f. Thus, the recursor for 0 is that, which constructs the canonical function from empty type to any other type. Logically, it corresponds to the principle ex falso quod libet. Okay. To construct a dependent function out of a coproduct, we assume as given the family and require Yes, we have like two dependent functions, one from A and one from B. So we have like this is the definition. If we package this to the induction principle, sure, gives us the way to define trivial dependent function of the empty type. Okay. That was short. The coproduct type is very short. The type of booleans 2. We have the type 0, 1, and 2. Well, I guess because 0 has 0 values, 1 has 1 value, and boolean is a 2 because it has 2 values. 2 elements, 0 and 1. It's clear that we could construct this type of the coproduct, and unit types is 1 plus 1. However, since it's used frequently, we give it the explicit rules here. Indeed, we're going to observe that we can also go the other way and derive binary coproducts from sigma types and 2. Yes. That's what I was saying. You don't need the enums if you have dependent pairs. Yes. To derive a function... Okay, this is just the booleans. I don't think this is any interesting. Natural numbers. So far we have rules for constructing new types by extrapolation by doing concrete mathematics. We also require some concrete types, such as types of numbers. The most basic such is the type and u of natural numbers. Once we have this, we can construct integers, rational numbers, real numbers, and so on. Yeah. The element of n are constructing using 0, n, and the successor operation suck. When denoting natural numbers, we adopt the usual decimal notation. The essential property of the natural numbers is that we can define functions by recursion and perform proofs by induction. Where now the words recursion and induction have a more familiar meaning. To construct a non-dependent function f and c out of the natural numbers by recursion, it is enough to provide a starting point and a next step function. Yes. We say that f is defined by primitive recursion. As an example, we'll look at how to define a function on rational numbers which doubles its argument. In this case, we have c doubles its argument, so c is the same as n. We first need to supply the value of double 0, which is easy. C0 is 0, sure. Double suck is suck suck. Okay. This indeed has the correct computational behavior. For example, we have double 2 is double suck suck 0. Is suck suck double suck 0. which is suck 0, which is suck 0. Of course, we're gonna find multiple variable function by primitive recursion as well, by currying and allowing C to be a function type. We're gonna find multiple variable functions by primitive control as well. For example, we define addition add this and the following starting point and next step data. As in previous cases, we can package the principle of primitive recursion into a recursor. Pattern matching and recursion. The natural numbers introduce the additional subtlety over the types considered up until now. In the case of coproducts, for instance, we could define a function f, a plus b into c, either with the recursor or by giving the defining equations. To go from the former expression to to go from the former expression of f to the latter, simply use the computation rules from the recursor. Conversely, given any defining equations where phi 0 and phi 1 are expressions that may involve the variables a and b respectively, we can express those equations equivalently in terms of the recursor by using the lambda abstraction. In the case of natural numbers, however, the defining equations of a function such as double involve the function itself on the right-hand side. However, we would like to be able to give these equations rather than 9, 1, rather than this. Yes. As the definition of double, since they are much more convenient and readable. Sure. The solution is to read the expression double n on the right side as standing in for the result of the recursive call, which in a definition of the form would be the second argument of CS. More generally, if we have a definition, hello, Robert Pattinson. How are you doing? More generally, we have a definition of a function f and into C such as f0 is phi 0 and f sec n is phi s, where phi 0 is an expression of type C and phi s is an expression of type C, which may involve the variable n, and also the symbol fn. We may translate it to the definition f is rec n, C, phi 0, lambda n, lambda r, A quote. How do you read this in math? Is it a quote? A quote is obtained from VS by replacing all occurrences by the new variable R. So this is just like the recursive definition of the function. But the recursion. It's 0 CS. Recursion is CU. We have C, which is the value for 0, and this, and yeah. Not much. We keep things smooth, no surprises. Just sometimes accidents happen, you know. Starting point and next step. Yes. Next step. Okay. If a programmer wrote such a function, it would simply call itself forever at any positive input. Hold on. Over here. This style of defining functions by recursion, or more generally, dependent functions by induction, is so convenient, but we frequently adopt it. It's called definition by pattern matching. Of course, it is very similar to how computer programs may define a recursive function with a body that literally contains a recursive calls to itself. However, unlike the programmer, we are restricted to what sorts of recursive calls we can make. In order for such definition to be re-expressible using the recursion principle, the function f being defined can only appear in the body of f sec n as the part of the composite symbol fn. Otherwise, we could write nonsense functions like this. f0 is 0. f sec n is f sec n. Yeah, I understand, yes. If a programmer wrote such a function, it would simply call itself forever. Could you explain the suck part? This is natural number. Suck means the next natural number. So, you know, like suck 0 is 1, and suck 1 is 2, and suck 2 is 3, and suck 4 is 5, you know? So a suck is n is basically n plus 2, right? So if you say that f n plus 1 is equal to f n plus 2, then it goes infinite recursion, right? You want to write here the something that's inductive, so it's using the previous values, not the future values, right? Actually, we only allow the previous value. We cannot have like n minus 1, for example, here. Wait, how do you do like a Fibonacci, for example? Explain it to your girlfriend. If a programmer, yeah, okay. This point will be even more important when we introduce more complicated inductive types in chapter 5, 6, and 11. We will produce a new kind of induction definition. We always begin by deriving its induction principle. Only then we do introduce an appropriate sort of pattern matching, which can be justified by as a shorthand for the induction principle. Propositions as types. As mentioned in the introduction, to show that a proposition is true in type theory corresponds to exhibiting an element of the type corresponding to that proposition. We regard the element of this type as evidence or witness that the proposition is true. So this is where we get to like the actual interesting part, I think. This is where we write proof. So in order to write a proof, we need an evidence, right? Evidence is basically the proof, right? Yeah, they are sometimes even called proofs. There you go. But this terminology can be misleading, so we generally avoid it. In general, however, we will not construct witnesses explicitly. Instead, we present the proofs in ordinary mathematical prose in such a way that they could be translated into an element of a type. This is no different from reasoning in classical set theory, where we don't expect to see an explicit derivation using the rules of predicate logic and the axiom as of set theory. However, the type theoretic perspective on proofs is nevertheless different in important ways. The basic principle of the logic of types theory is that a proposition is not merely true or false, but rather can be seen as the collection of all possible witnesses of its truth. Under this conception, proofs are not just the means by which mathematics is communicated, but rather are mathematical objects in their own right, on a par with more familiar objects such as numbers, mappings, groups, and so on. Thus, since types classify the available mathematical objects and govern how they interact, propositions are nothing but special types, namely types. Those elements are proofs. Yes. Types classify the available mathematical objects and govern how they interact. The basic observation which makes this identification feasible is that we have the following natural correspondence between logical operations on propositions expressed in English and the type theoretic operations of their corresponding type witnesses. English, true is 1, false is 0. A and B is A x B. A or B is A plus B. If A then B is a function from A to B. A if and only if B is two functions from A to B and from B to A. There is a recent post called Propositions as Types on Hacker News. What are the odds? Yeah, I guess this is not a new idea. Propositions as types. News. I think propositions as types is exactly why we should consider proofs to be the same if they prove the same type. Is this the same? Is this the thing? I don't know how to use this website. Propositions as types. 2014 PDF. Wait, isn't this book literally from 2014? Oh, that's a different one. Brown, brown. The point of the correspondence is that in each case, the rules for constructing. Can you send the link to that sneakers makeover? What? What sneakers makeover? Sneakers makeover sourced from the original camera negative. I mean, it's just on the front page of the Hacker News. Oh, there you go. What's Sneakers 1992? Is that a movie? I think I've seen this one. The point of corresponds to, in each case, the rules for construction and using the elements of the type on the right correspond to the rules for reasoning about the proposition on the left. For instance, the basic way to prove a statement of the form A and B is to prove A and to prove B, while the basic way to construct an element A and B is a pair A and B, where A is an element or witness of A and B is an element of witness of B. If we want to use A and B, if we want to use A and B to prove something else, we are free to use both A and B. In doing so, analogously to how the induction principle for A and B allows us to construct a function out of it by just using elements of A and of B. Similarly, the basic way to prove an implication, if A then B, is to assume A and prove B, while the basic way to construct an element of a function A into B is to give an expression which denotes the element witness of B, which may involve an unspecified variable of type A. And the basic way to use an implication if A and then B is to deduce B if we know A. Analogously, how we can apply a function f from A into B to an element of A to produce the element of B. We strongly encourage the reader to do the exercise of verifying the rules governing the other type construction to translate sensibly into logic. So I'm interested in this one. If A, if only, if and only if B. I mean, if A then B and if B then A. I mean, yeah, that makes sense. All right. On a special note is that the empty type 0 corresponds to full city. When speaking logically, we refer to an inhabitant of 0 as a contradiction. Thus, there is no way to prove a contradiction. While from a contradiction, anything can be derived. We also define a negation of a type A as not A. We define negation of type A as not A, which is a function from A into nothing. Thus, a witness of not A is a function A into nothing, A into 0, which we may construct by assuming X and deriving an element of 0. A witness of this is a function that which we may construct by assuming X, A, and deriving an element of 0. Note that although the logic we obtain is constructive, as discussed in the introduction, this sort of proof by contradiction. Assume A and derive the contradiction, concluding not A is perfectly valid constructively. It is simply invoking the meaning of negation. Oh, I see what this means. Yes. So like not a means that a function a into 0. So this means that like if we actually have the element of a, so like if a is true, then we would be able to have 0, and 0 has no elements in it. So it's a contradiction, right? Which means that there is no element here, so this is an empty set. Yeah. So it's false. Or 0, 2, right? Because the only way to construct a 0 is from another 0. Proof by contradiction. Sort of such argument would only allow us to conclude not a, and the reader can verify that there is no obvious way to get from not a to a. The above translation of logical correctness into type forming operations is referred to as propositions as types. It gives us a way to translate propositions and their proofs written in English into types and their elements. For example, we suppose we want to prove the following tautology. If not A and not B, then not A or B. An ordinary English proof for this fact might go as follows. Suppose not A and not B, and also suppose A or B. We will derive a contradiction. There are two cases. If A holds, then cis not A, we have a contradiction. Similarly, if B holds, then cis not B, we also have a contradiction. Thus, we have a contradiction in either case, so not A or B. Now, the type corresponding to our tautology, according to the rules given above, is so this is not A, and this is not B. This is not A or B. So we should be able to translate the above proof into an element of this type. Yes, so like this is the type that we need to construct in order to prove this, right? In order to prove this, we need to construct this thing. So we need to construct a function with this signature. An example of how translation works. Let us describe how a mathematician reading in the English proof above might simultaneously constructing that had an element. The introductory phrase, suppose not A and not B, translated into defining a function with an implicit application of the recursion principle from the Cartesian product and its domain. This introduces unnamed variables, hypothesis of types, not A and not B. And when translating into type theory, you have to give these variable names. Let us call them X and Y. So this is the definition. This is how we define this, right? So if I have X and Y, X is basically the proof that A is false. And this is proof that B is false, right? So we have those two proofs. Then we can do this thing. So this is an empty thing. This is a whole of type, indicating that it remains to be done. Okay, a whole, okay, sure. We would equivalently write this using the recursor instead of pattern matching. In the next phase, also suppose A or B, we will derive a contradiction. Indicates that filling this whole by a function definition introducing another unnamed hypothesis. Z as A plus B leading to the proof state. Now saying there are two cases. Now, saying there are two cases indicates a case split. An application of the recursion principle for the coproduct a plus b. If we write this using the recursor, this would be that. While if we write using pattern matching, it would be this. Okay, now that in both cases we have two holes of type 0 to fill in. Yes. So like we can construct 0 by x is a function from a into 0. Yeah. So we just call x with a, and over here we call y with b. There we go. And this is basically the proof. That's how you should verify the converse tautology exhibiting the element. For types A and B using the rules we have just introduced. However, not all classical tautologies hold under this interpretation. For example, the rule, if not A and B, then not A or not B is not valid. We cannot in general construct an element of the corresponding type. This reflects the fact that natural proposition as types logic of type theory is constructive. This means that it does not include certain classical principles such as the law of excluded middle. Or proof by contradiction. And others which depend on them, such as this instance of De Morgan's law. The philosophically constructive logic is so called because it confines itself to construction that can be carried out effectively. Just to say those with a computational meaning. Without being too precise, this means that there is some sort of algorithm specifying step by step how to build an object, and as a special case, how to see that a theorem is true. This requires our omission of Lem, law of excluded middle, since there is no effective procedure for defining whether a presupposition is true or false. The constructivity of type theoretic logic means that it has an intrinsic computational meaning, which is of interest to computer scientists. It also means that the type theory provides axiomatic freedom. For example, while by default there is no construction witnessing law of excluded middle, the logic is still compatible with the existence of one. Thus, because type theory does not deny LEM, we may consistently add it as an assumption and work conveniently without restriction. In this respect, type theory enriches rather than constrains conventional mathematical principle practice. We encourage the reader who is unfamiliar with constructive logic to work through some of the examples as a means of getting familiar with it. So far we have discussed only propositional logic. Now we consider predicate logic, where in addition to logical connectives like a and or, we have quantifiers there exists and for all, which is the dependent function and dependent pair. For all x of a, px holds. Yes. There exists x a such that px. Yes. I mean, this actually makes sense. Yes, this makes sense. We say there exists x of a by like just constructing an example. All right. Just types. As before, we can show the tautologies of constructing practical logic translate into inhabited types. For example, if for all x, a, px, and x and qx, then for all x, a, px, and for all XAQX translates to this. Sure. And informal proof. Oh, this is, yeah, this is okay. This is easy. As a more concrete example, consider how to define inequalities of natural numbers. One natural definition is that n is less than or equal to m if there exists a k such that n plus k is m. This uses, again, the identity types that we will introduce in the next section, but we will not need very much about them. Under the propositions as types or translations, this would yield n is less than or equal than m is sigma of a k where n plus k is m. Wait, what is n plus k is m? So a plus is the co-product. What's the equal? So the equality also like needs to be proven, right? How do we define equality? This uses again the identity types that we will introduce in the next. Oh yeah. So like equality is the identity type. All right. Now this is all making sense now. Yes. So like equality is a type, and if we can like have the value of this type, then it means that it's true and the things are actually equal, right? Yeah. Okay, this makes sense. Under the propositions as types translation, this would yield. The reader is invited to prove that the familiar properties of this from this definition for strict inequality, there are a couple of natural choices, such as, so if we have less than or equal, then less is something where we add suc n, sure. So we need to either prove this, or we need to prove that they are less than or equal and not equal at the same time. The former is more natural in constructive mathematics, but in this case it's actually equivalent to the latter. Really, that makes sense. I just understand Autobahn. The controlled access highway system. Are you referring to something else? What do you mean understanding Autobahn? Numbering system, maybe this? Autobahn numbering system? I don't understand Autobahn. Just a wordplay for government to say I do not understand anything. All right. So basically, this thing says that we can prove things. So like we're making a programming language, right? And in a programming language, you need to maybe you would need to prove some things, right? So so in order to prove something, you need to supply evidence, right? So the evidence is basically a value of a type, which is like so the type is basically the theory, and if you have the evidence, then the theory is true, kind of, I guess, right? So I get so, and this is how like proof assistants work, I guess, like languages like Coq or something, maybe. I don't know. I don't know really. But like you would need to do this if you are writing like, I need to explain far above my understanding. Don't want to interrupt. No worries. No, if I try to explain it and you understand that, it means that I understand it, right? and not lying to myself that I'm understanding it, right? But yeah, by having propositions as types, we can program the proofs in our programming language where when we need to prove something. Oh, we'll return to this. Where was I? The former is more natural in constructive mathematics, but in this case it is actually equivalent to the latter, since n has decidable equality. There's also another interpretation of the type, sigma x apx, since an inhabitant of it is an element x a together with a witness that px holds. Instead of regarding this as a proposition, there exists x such as that px, we can regard of it as the type of all elements x such that px, which is a subtype of a. Wait, what? This is a type of all elements x a such that px, a subtype of a. Oh no, I understand. Yeah, okay. The type of this is the type of all elements, not the value of this is the type. Yeah, the value is not the type. So this thing is a subtype of a because it's a plus something else. All right, sure. We will return to this interpretation in 3.5. For now, we note that it allows us to incorporate axioms into the definition of types as mathematical structures, which we discussed in 1.6. For example, suppose that we want to define a semigroup to be a type A equipped with a binary operation, AAA, that is a magma. Is magma like a thing? Magma math. Magma is a set equipped with a single binary operator. Yeah. That's literally what it is. What's a semigroup? I remember groups a little bit, but I don't remember exactly what it is. So a semigroup is a structure consisting of a set together with an associative internal binary operation on it. Okay. What's a group? What's a group? A set together with a binary operation that satisfies the constraint, the operation is associative. Okay. It has an identity element and yeah, okay. I see. Wait, what's a semigroup? Associative internal binary operator. And what's a magma? Isn't this the same as a magma? The graphic is wild with a semigroup. No worries. Here's this tesseract of the associated concepts. Yeah. I mean, algebraic structures between magmas and groups. Wait, hold on. So there's a magma. And then there is the group. And then there is the semigroup. And then there is an arrow from a magma into a semigroup with associativity. Wait, does a semigroup... Oh, it's... Oh, yeah, semigroup is like an associative operation, right? So that's like the difference between a magma and a semigroup. Yeah, that makes sense. Magma? Magma balls? All right. Whatever. A semigroup is a type yeah, so like a semigroup is a magma where for all x, y, and z we have mx is this, like, so like this means that it's an associative operation, right? So like a semigroup is a magma where the operation is associative. So we need to prove that this, right? So the letter proposition, so if we want to actually prove this, then we need to have this type, right? So this is the type that represents the proposition, right? So for all x and y and z, this is equal to that. So the type of the semigroups is, so a semigroup is this. The type A, the operation plus the proof that the operation is associative, right? That's what a semigroup is. Yeah, that makes sense. Axioms are just the most basic. Yeah. Yeah, it's all easy. It's all easy now that I think about it. It's all easy. The subtype of magma consisting of semigroup. Yeah, so like the semigroup is a subtype of magma. Sure. From an inhabitant of a semigroup, we can extract the carrier A, the operation M, and a witness of the axiom. Yes, by applying the appropriate projections. We will return to this example. Now that we can use the universes in type theory to represent higher order logic. That is, we can quantify over all propositions or over all predicates. For example, we can represent the proposition for all properties P so for all properties P, AU, if the A, then PB as this. We can use the universes in type theory to present higher order logic. We can quantify all proposition or all over all predicates. So like U means like U is basically at any type, right? It's a universe. So these are like helper, yeah, higher order logic means like helpers, I guess, for proofs, right? So yeah, basically if we know that if A then something, I mean, this is a property. Yeah. Down. Where AU and AB is A. However, a priori, this proposition lives in a different higher universe than the propositions we are currently quantifying over. Okay, so like I guess because we are using the universe here in the definition of this type, the type of this is U plus 1, so we cannot prove this with itself. We cannot use itself. We have U as the type of truth values. Yeah. Well, a type is a proposition, so like U is like any proposition, basically, right? We have described there a proof-relevant translation of propositions where the proofs of disjunctions and existential statements carry some information. For instance, if we have an inhabitant of A plus B regarded as a witness of A or B, then we know whether it came from A or from B. Similarly, if we have an inhabitant of sigma xpx regarded as a witness of there exists x a. Similarly, if we have an inhabitant of x of a sigma xapx regarded as the witness of there exists x such as that px, and we know that the element x, then we know what the element x is. Yes, we know, yes, of course. We know what it is. As a consequence of the proof-relevant nature of this logic, we may have A if and only if B, which is A then B and B then A. Guys, check this out, P. And yet the types A and B exhibit different behavior. I'm wondering, wait, how do you write math? How do you write math? Is it like an emoji? How do you write this? How to write math symbols? Do you need a special keyboard for this? The LaTeX, yeah. And then you just have like the backslash with like the things. But like if you're not using the LaTeX, then is there a way? An easy way? I never set up like even the emojis. I remember that on Windows I could like easily like do like Windows dot and then I just search for an emoji, and maybe like the math symbols are also there. I should like set this up on my Linux somehow too. Unicode what's painted doesn't even look nice. Well, I mean, I guess, yeah, like over here we want subscripts and shit, right? But when you're like, when you're writing a program in a programming language, you will not have like the subscripts, right? But sometimes, I don't know, maybe you want the symbols, right? Like in APL or something. Like, how do people write this language? They don't write it with LaTeX, right? But they use all kinds of symbols here. Or it's just like an autocomplete in the editor. That's supposed to do that. The ASCII shortcuts and the yeah, I guess it's the editor's job. Sure. It's called character map on Windows. Yeah, I want the character map. Mostly for emojis though, not for math. I would rather prefer seeing this as an exists actually in code, and the P as for all in code, like as a keyword, instead of it being a symbol. For instance, it is easy to verify that an, if and only if one, and yet clearly n and 1 differ in important ways. The statement tells us only that when regarded as a mere proposition, the type n represents the same proposition as 1. Yeah, so like, yeah, sure. They are logically equivalent. This is to be distinguished from the stronger notion of equivalence of types to be introduced. Okay, although n and 1 are logically equivalent, they are not equivalent types. In chapter 3, we'll introduce the class of types called mere propositions, for which equivalence and logical equivalence coincide. So, I mean, a mere proposition would be something that's equivalent to 1, I guess. So it only has a single element, right? That would be a mere proposition. Modification to the above described logic that is sometimes appropriate, in which the additional information contained in disjunction and existentials is discarded. Finally, we know that the proposition as types correspondence can be viewed in reverse, allowing us to regard any type A as proposition, which we prove by exhibiting an element of A. Sometimes we will call this proposition A is inhabited. That is, when we say that A is inhabited, would mean that we have given an element of A. But we are not choosing, but it would mean that we have given an element of A, but that we are choosing not to give a name to that element. Similarly, that A is not inhabited is the same as to give an element of not A. In particular, so an element of not A is like a function from A into 0, which like basically a map from A to 0, right? Yeah. Identity types. Well, the previous construction has been a generalization of standard set theoretical constructions. Our way of handling identity seems to be specific to type theory. According to the propositions as types conception, the proposition has the proposition that two elements of the same type, A and B, are equal must correspond to some type. The proposition that two elements are the same must correspond to some type. Since the proposition depends on what A and B are, this equality types or identity types must be type families dependent on two copies of A. Yes. We might write the family as ID A into U, not to be mistaken for the identity function. Yes. So that ID A and B is the type yeah. Why was this like introduction to Hot starting with this? That makes no sense to me. All right, but now it does make sense. And also I remember that they started A into B into U, I think, right? Or was it not? No, maybe it's all, yeah, it's always the same. How would we prove that two elements of different types are different? That would be weird, right? Yeah, it's all, both of them are of type A, sure. We can only prove the equality of the values of the same type. Down, down. For clarity, we may also write A is equal to B of type A, right? But I guess like we can say just equal without A, if we can infer it, right? We may say that A and B are equal or sometimes propositionally equal if we want to emphasize that this is different from judgmental equality. Just as we remarked, the propositions as types, versions of or and there exist can include more information than just the fact that the proposition is true. Nothing prevents the type A and B from also including more information. Indeed, this is the cornerstone of homotopical interpretation, where we regard the witness of A as B as paths or equivalences between A and B in the space A. Just as there can be more than one path between 2 points of a space, there can be more than one witness that 2 objects are equal. Put differently, we may regard A as B as the type of identifications of A and B, and there may be different ways in which A and B can be identified. We will return to the interpretation in chapter 2. For now, we focus on the basic rules for the identity type. Just like in all other types, considering on this chapter, we will have rules for formation, introduction, elimination, and computation, which behave normally. By the way, like, so still the only question that I had throughout the entire book was the the uniqueness, and they they have not been using uniqueness since they have like introduced what it means, kind of. So I still don't understand it. They only use formation, introduction, elimination, computation. Because uniqueness is like not always necessary, right? It's an optional one. Right, we'll see. The formation rule says that given a type A, U, and 2 elements A, B, we can form a type A is equal to B in the same universe. The basic way to construct an element of A equals to B is to know that A and B are the same. Thus, the introduction rule is a dependent function. Introduction rule is a way to construct an element of A is equal to B. So we need to like know that A and B are the same. The introduction rule is a dependent function. The introduction rule is a dependent function. For all A is equal to A, called reflexivity, which says that every element of A is equal to itself in a specified way. Given 2 elements, A and A, we can form the type A is equal to B. Formation rule is not the constructor. This is just like the type, right? This is a way to denote the type, I think, right? So like this is how we denote the type. This is supposed to be the constructor. And we should have like multiple constructors. There are, I guess, right? So there is a reflexivity, which is this. In particular, this means that if A and B are judgmentally equal, then we also have an element ref A is B. This is well typed because A is equals B. Means that also the type A is B is judgmentally equal to the type A and A, which is the type of raffle A. Hold on. I don't understand this yet. The induction principle for the identity types is one of the most subtle parts of type theory and crucial to the homotopy interpretation. We begin by considering an important consequence of it. The principle that equals may be substituted for equals, as expressed the following. Indiscernibility of identicals. For every family, C A to U, there is a function for all x and y of A, for all P, which is the evidence that x is equal to y. If this then that, because they are equal. That makes sense, but like in this case, it's not really like if this is not a proposition but just some type. Yeah, so like I guess so we have a function that calculates some value, right? And this means that if I call the function with another element, with another argument, which is same as the argument with which I have calculated the function before, then the result is going to be the same, right? That's what it means. Equals may be substituted for equals, basically. Yeah, that's what it means. Such that fxx raffle x is id cx. What? This is a requirement? This says that every family of type C respect equality in the sense that applying C to equal element of A also results in a function between resulting types. The displayed equality states that the function associated with true reflexivity is the identity function. The displayed equality states that the function associated to reflexivity is identity function, and we shall see that in general the function f x y p is always an equivalence of types. The equivalence of types. Indiscernibility of identicals can be regarded as a recursion principle for the identity type, analogous to those given for booleans and natural numbers above. This rec_n gives a specified map and to C for any other type C of a certain sort. Indiscernibility of identicals gives a specified map from X is A to certain other reflexive binary relations on A, namely those of the form Cx into Cy. Some unary predicate Cx. We could also formulate a more general recursion principle with respect to reflexive relations of the more general form. However, in order to fully characterize the identity type, we must generalize this recursion principle to an induction principle, which not only considers maps of X out of this, but also families over it. Put differently, we consider not only allow equals to be substituted for equals, but also taking into account the evidence for equality. Path induction. The induction principle for the identity type is called path induction. In view of the homotopical interpretation to be explained in the introduction to chapter 2, it can be seen as stating that the family of identity types is freely generated by the elements of the form. The family of identity types is freely generated by the elements of the form refl x. X equals x. Path induction. Given a family C for all x and y of type A, x equals to y, then u. So we have this family. And a function C for all xa, cxx reflex, cxx reflex. Reflex is the yeah, this is the evidence that x is equal to y, yes. we have this function. So this is the function that for x, for all x's of type A, returns some type. There is a function f for all x and y of A. For all proofs is like predicate over equality. Proofs between x and y. C is a predicate. Well, I mean, if we like, I mean, if we say that u, like if we only think about u here as like a proposition, right? Then it is a predicate, right? But like in theory, this can be any type, right? It's not like u is not just the universe of propositions, right? So it's not exactly a predicate. Like, but I don't know. I mean, if we think about this only in the context of like logic, I guess, and if we only have like predicates here, you always think of it that way. I mean, I don't know. Maybe it's useful to think about this for some reason. Like maybe this can be useful for something else than just logic. I don't know. But it does make it clear. Yeah, I agree with that. Maybe like why is this a universe? When you are writing this like as a program, right? When you're writing proofs, I'm assuming languages like Coq, right? I don't know like what other languages do this, right? Like Agda, I guess, or whatever. I never tried languages like this, but like, do you have like, isn't it worth to have like separate universe for like the types and then separate universe for like propositions then? Well, I guess if your language, all it probably does is just, if it's just a proof assistant, then like having this as just the universe of all propositions makes sense. But if it's like a language that you use for other things, I guess. Like if I'm making my own language, I would probably make the propositions to be a separate universe. Maybe. I don't know yet. And a function C. There's a function for x. Such that f x is cx. Note that just like the induction principle, for products, co-products, natural numbers, and so on, path induction allows us to define specified functions. Wait, yeah. So like this is supposed to be the induction principle. The induction principle is allows us to define specified functions which exhibit appropriate computational behavior. Induction principle. So what is induction principle? It's just like a way to have a dependent function from the thing, right? This thing. And when you like from this value, I really don't see what makes sense. What makes mirror propositions so special among all types? Types will literally correspond to spaces of all proofs. I mean, yeah, they are not really special, but like when you're reading code, like it's I mean, if like it would be more obvious when I'm just reading code, I guess. You know, like I don't know. Yeah, it's just like like a different naming, you know. Like you have the sigma type, right, which is a dependent pair, right? But you don't say that it's a dependent pair. You say there exists this such that when you are writing logic, right? It still is just a dependent pair, right? But you don't think about it as such, right? So yeah, not really like special, but it's just written differently and said differently. So why should it look the same? Like, you know, even though the implementation is the same. Representation just means to make the translation to logic explicit and formal. Yeah. Hold on, this over here I am having trouble with so far. To understand the meaning, consider the first simpler case when C does not depend on P. When C does not depend on P. Then we have C is A into U. Oh, P is like the proof that they are equal. So if it doesn't depend on that, and C is just that, which we may regard as a predicate depending on two elements of A. We're interested in knowing when the proposition C you walked away to shower, but from what I gather, these types that establish other are not really useful for general programming and would typically be useful for proofs, which should probably be a special part of the local problem. Can you explain why they are in the same universe in theory? These types that establish others not useful. Oh, I mean, no, the types, they're not really like any special. You want that the dependent functions, dependent types are useful in normal programming, but they are essential for proofs, I guess, when you have propositions as types. Right? Like you have functions, right? Functions are used for logic. So a function, you obviously use it in normal programming, right? But when you're writing a proof, if you need to prove that if A then B, then you need to construct a function from A to B, right? Consider the first simpler case where C does not depend. We have C, A, A, U, which we may regard as predicate depending on two elements of A. Yes, but like if we like, so okay, so if we are talking about predicates here, predicate depending on two elements of A. Yes, but like, what is two elements of A? If A is a type, which is a proposition, right? What does it mean to have two elements of A, right? It means that I have proven A twice, which is completely useless, right? So, so, and then if C depends on the proof that two things are equal, but we still have two proofs here. So like, this is still useless, no? Like, what are we trying to say here? Like, it depends on the, like, it depends like on how we proved that these are equal. Like, what are we trying to do here? I don't understand. Which we may regard as predicate given the two elements of A. You are interested in knowing when the proposition CXY holds for some pair of elements XY. In this case, the hypothesis of path induction says that we know CXX holds for all X. That if we evaluate C at the pair XX, we get a true proposition. So C is a reflexive relation. This conclusion then tells us that CXY holds whenever X is equal to Y. This is exactly the more general recursion principle for reflexive. No, because the proofs may be different and they might compose differently. Yeah. Different proofs might interact differently. But like, what does this mean even? Like, I don't get it still. The meaning of this principle. Or is it in knowing when the proposition CXY holds? Like, what does it mean? Like, why am I interested in this? So it's a predicate depending on two elements of A. Okay, maybe in this case we don't like. I mean, maybe it's because I was thinking that A is also a proposition, you know? Because like, if you think about these things as propositions, then what does it mean to have like different two different elements, right? Because it's weird. Like, a proposition is supposed to be a type that is like inhabited and it has only one single element, no? If it's like a mere proposition, right? So it only has a single element, I think, right? So maybe this is a predicate that takes not propositions as arguments, but just two elements, right? For example, this is a predicate saying that I don't know, 2 equals to, like 2 is less than 3, right? So this is a natural number, and we want to prove that, right? Or something. And what would this mean then? So we have like 2 things. If they are equal, and that. The general inductive form of the rule allows C to also depend on the witness of X being equal to Y to the identity between X and Y. In the premise, we do not only replace X, Y by XX, but also simultaneously replace P by reflexivity to prove a property for all elements X and Y. To prove a property for all elements X and Y and paths between them, it suffices to consider all the cases where the elements are XX and the path is reflex. If we were viewing types just as sets, it would be unclear what this buys us. But since there may be many different identifications between X and Y, it makes sense to keep track of them in considering families over the type X is equal to Y. In chapter 2 we will see. The idea is that if you know that CXX for all X, then it already holds for all CXY for any XY. All because C is a function from the path space. For any X and Y that are equal, right? It's not for all X and Y, but only for those that are equal. But like, how is that useful? Like, I don't understand what this gives us. I don't understand why are we doing this here. If we package up path indication into a single function, it takes the form. So this is the induction for equality. So induction for equality is the path induction. Is CX. The function is traditionally called J. We will show in lemma 231 that indiscernibility of identicals is an instance of path induction. This is because X is equal X does seem much easier to prove than X equals Y. Is easier to prove than X is equals to Y, but you need to prove that X equals to Y to like get this anyway, right? Because that's the argument to over here. Like, if it's easier to prove, how does it matter? Since we still need to prove that X is equal to Y. This is called J. Given a proof P, A equals B. Path induction requires us to replace both A and B. Path induction requires us to replace both A and B with the same unknown element X. Thus, in order to define an element of a family C, all pairs of equal... So, yeah, for all pairs of equal elements of A... Wait, what do you mean for all pairs of equal elements of A? Is like different elements still equal? Wait, what is equality? So he takes those proofs as arguments, but I'm not sure that we need to supply such a proof. Well, if you want to use the induction principle, right? Or you're saying that we don't... I don't know. Well, I mean... Path induction requires us to replace both A and B with the same unknown element X. Thus, in order to define an element of family C, for all pairs of equal elements of A, it suffices to define it on the diagonal. Yes. In some proofs, however, it is simpler to make use of the equation P A is B by replacing all occurrences of B with A, because it is sometimes easier to do the remainder of the proof for the specific element A mentioned in the equality rather than for general unknown X. This motivates a second induction principle for identity types, which says that the family of types A which says that the family of type A equals X is generated by the element raffle. A is A. As we show below, this second principle is equivalent to the first. It is just sometimes a more convenient formulation. When we give such a C to int, we give nothing to C ourselves. Well, yes, we don't give it ourselves when we define the induction principle, but when we use the induction principle, we are going to need to supply the proof, right? To use the well, like, what is the induction principle used for? Well, it's used for proving things, right? The induction principle is literally a function. We only supply things of the form x equals x, and that suffices. Well, I mean, hold on. What is an induction principle at all? Induction principle is a way to get rid. So, like, basically, if we have the proof that this is equals, right? That's literally it, right? This is what we need, right? If we have a proof that x is equal to y, then we need to get something. Right? So, yeah, so induction principle means that we need to be able to... so that's why it's called induction, right? If we have some proof, we can prove something else, right? That's why. So the induction principle for the equalities is this, because that's what we're defining right now. Right? Proof path induction requires us to replace both A and B. Based path induction. C. Fix an element A, and suppose given a family, which is that, and an element C. C A raffle A. Then we obtain a function x a for all here a is x, c x b, such that f a raffle a is c. Here c x b is a family of types where x is an element of a and p is an element of the identity type a or fixed a. Based path induction principle says that to define an element of this family for all x and p, suffices to consider just the case where x is a, p is raffle a is a. Here's a function based induction becomes this. Yeah. We just flip the argument. Where is the argument? We move the a to the beginning here, right? Yes. So this like y or whatever x, one of them is moving to the beginning. Doesn't it say that you only need that little c which only knows about those equalities? Yes, but this is like so like you need the little c to construct the induction principle itself, right? So like to construct the induction principle, you only need to know the reflection, right? Something. I don't know. I'm not sure. This identity types is the most difficult one. I mean, I understand what the type means, but like the these principles, I'm not sure yet. Let's see, is the proof of the induction hypothesis needs to begin induction. Hmm. Oh, this is how, okay, this is how you begin induction. Nah, hold on. Based path induction, we have this thing. I mean, in order to use the induction principle, we provide with a function that says like if two things are equal, I guess it's something is equal to A in this case, then something. Oh, maybe you're right. Maybe you're right. This is what we get, yeah. And the induction principle then proves that these things are equal. Yeah, then with it you prove C for all x equal y. Yes. You're right, I think. Equivalence. The two induction principles for the identity type introduced are above are equivalent. It is easy to see that path induction follows from the based path induction principle. Indeed, let's assume the premises of path induction. Now, given an element x of A, we can instantiate both of the above. Given an element x, we do this, and this match the premises of the base path-based induction with the inequality. Now they observe that G codomain is equal to C xyp, thus discharging our assumption xa. We can derive a function with the required judgmental equality. Another proof of this fact is to observe that any such f can be obtained as an instance of this, so it suffices to define this in terms of that. So this is the path induction, this is based path induction, right? So you can define one in terms of the other. Yeah. The other direction is a bit trickier, but you can still do it. Okay, I mean, sure, I will believe that it's true. Finally, let's also say something about disequality, right? So sometimes we want to prove that two things are not equal, which is the negation of the equality. If x is not equal to y, we say that x are unequal or not equal. Just like negation, disequality plays a less important role here than it does in classical mathematics. For example, we cannot prove that two things are equal, but proving they are not unequal. That would be an application of the classical law of double negation. Sometimes it is useful to phrase this equality in a positive way. For example, we shall prove that a real number x has an inverse if and only if its distance from 0 is positive, which is a stronger requirement than x is not equal to 0. And there's exercises. Given functions f, a into b, and g, b into c, define their composite gf, which is a into c. Show that we have hgf equal to hgf. Define their composite. GF. So, oh, okay. So I see. So the composite needs to be defined. So in order to define something, we need the four things, right? The formation rule is that G the formation rule is just this, right? The formation rule just says how do we write things. Is that correct? So that's how we write the composition of functions. That's the constructor. Right? And its type. Um, so the type would be A into B, B into C. Or like, do you not specify this? So this is a constructor, right? This is a constructor or whatever. And the formation intervals is basically exact first. The introduction rule is the constructor, so like this thing. Right? This is the introduction. And the type is A into B, A into B, like, and then like some symbol B into C or something. Maybe, I don't know. Is that what we're supposed to do there? And then we need like the principles. The type is A into C already. Okay. Okay, sure. So like, okay, so this is the type. Okay. Sure. So we need to define the principles, right? Wait, so where's the list of things that I need to define? Introduction, foundation. These are the things, right? Introduction rule. How to use elements of that type. Eliminator. Well, I mean, I don't think the type is A into C because like it's like we're supposed to define it separately, no? Like A into C is basically is a function, but we're supposed to define composition as like as a separate type, kind of, right? That's what we're supposed to do. So it's not a into C, is it? Because A into C is how you form a function, but we're not forming a function, we're not forming a function composition, right? As a separate type, I think. That's what the exercise is trying to do, no? You define individual composites of two specific functions. You should define individual composites of two specific functions. No, I think it's supposed to be a general one. Like, like I guess like so a function type is written as A into B, where A is a type and B is a type, right? So A is U and B is U, right? But the but for the function composition, let's do it with dot, right? So for the function composition, we need like function f is A into B, right? And then function g is B into C, right? Where A is U and B is U. No? There's no special kind of composition type. Wouldn't those just be ordered pairs anyways? Ordered pairs of composable functions? Yeah, but like, isn't the exercise supposed to be just ordered pairs, composable functions? I mean, the exercise is trying to well, I mean, it's not just any ordered pair, right? It's a specific ordered pair, right? So like, it's basically like something like for all A, I guess we can do this, A and B of U, and then we say like for all F is this and G is this. Or what do you want, like with a dot here? We just say F dot G, and that's like the type. No? I interpreted it as define the composition operator. Well, I mean, what's the exercise supposed to be about? I'm supposed to instructions, eliminators, computation. Like, these are the things that we need to do, right? How to eliminate a function composition, right? So this is like the type, this is the thing. I don't know, maybe I'm doing something wrong completely. So we need to have the so for example, the computation rule, right? Or I mean, like how to use the element, right? So in order to use the element, it is like applying a function, right? So we just do fg like with some argument x. X, which is a, right? That's how we use it. And then we define how we use it on a constructor. So f dot g with x is basically equal to g fx, right? That's how we're supposed to do it here. And then so like I think this is all that is needed. No. So we eliminate the this is the elimination principle. We eliminate this thing, right? And then the other part of the exercise is that we want to prove that it's the associative operation, right? So here's and this is where we get to the proofs, right? We want to show that it's associative, right? So the type of this would be h g dot f should be equal. Wait, this is a triple equality, which is different. Show that g am I supposed to like prove this? What is the triple equality? It's the judgmental equality, right? How do you prove judgmental equality? From other judgmental equalities? I don't think I remember any example of that. How am I supposed to do this exercise? The uniqueness principle are sometimes considered for other types. For instance, the uniqueness principle would be a judgmental version of the propositional equality. We construct in 1.5, saying that u is equal to this. Wait, what? 1.5 product types. What did we do here? We're supposed to judgmentally define fgx is equal to gfx, and the rest follows. Well, I mean, this is so this is like this is the eliminator, right? So using this thing, we can prove that thing, right? Or something. I mean, is it just the like rule? Like it's not like a programmatic proof, right? So we just say that if I have HGF, right, then we just use this rule already, right, which we already have, which would be G dot F or I guess like this with X is GF with HX, and then this is or I guess it's like, I think this is not even correct. I think we're supposed to do something like this: f and g is equal to lambda x into gfx, right? Like I'm not supposed to have any extra arguments here, right? So that we can actually rewrite this. I'm not sure. Right, because lambda is the way to form a function, and then we like use the elimination principle for the function, right? So when we have a function here, right, what's the function's elimination principle? So this is also something that was confusing, right? Where this is equal to that, right? The function is which is the elimination principle. I think elimination principle was just saying that we rewrite this, right, by replacing like argument with the thing, right? That's literally it, I think. A little bit above. I don't see the word elimination here. That's what I'm looking for. It's called some computation rule. Oh yeah, it's a computation rule, right? Computation or elimination is the same thing, right? Now we can compute f by replacing the variable x in f with a. That's it, right? So now, since we have wait, what? Or maybe I don't even need to do anything here anymore. Maybe all we need to see is like h dot g dot f and see what this becomes, right? Down, down. So x. So in this case, we would apply this first to h dot g with x, and then we call function f with it, right? Which we then rewrite this with lambda y into ghy. So over here we have a lambda, and we call the lambda with x. So we just replace y here with x, right? That's the computation rule. So we replace this y with x, right? And we just have f g hx, right? That's it. And then we can do the same thing over here, right? Because we over here y is equal to hx, so we just replace this with that and remove that, and we have the same thing, right? So is this what I need to do? So now I have shown it. Not a big Twitch chatter usually. That is great to see people learn mathematics. I'm making my own programming language, so that's why I've been researching this. I like the idea of dependent types and stuff. I wanted to see what else is there. The I guess the proof assistant is going to be included in my language too. So we don't need to simplify this even further because there is nothing else to simplify, right? Because I don't actually apply this lambda to anything else. Yeah, that's it. So now it's the same, yeah. Right. I think this is good. I'm going to maybe read this next time. Then I went through the type theory here. There's more exercises that I could try, I guess. But and to end the stream for today. And next time I can do homotopy type theory. See what that is about. It's kind of fun. Not sure how to put it to use yet, though. Exactly. Downtown. But I mean, we need to we will need to write proofs for the functions to compile, right? In a dependently typed language. All right. Let's just go to Edward here. This guy knows all the math already. Why is nothing loading for me? Why is nothing loading for me? Hello? Of course he's solving Sudokus. Alright. Next time, bye.